Everything solid around you is behaving according to an equation that no one has ever truly seen. It predicts the color of every atom in your body, the chemistry inside your brain, and the light reaching your eyes with astonishing precision. After a century of experiments, it has never once been caught making a wrong prediction. Yet the man who discovered it spent the rest of his life refusing to believe what it was telling him about reality. Most explanations begin with the finished equation. Tonight, we will do the opposite. We will begin with just two simple measurements, then quietly watch the Schrödinger equation emerge, one clear step at a time, until you could rebuild it for yourself. Stay with us through the quiet hours. Before this journey is over, we will watch a wave become mathematics, see an atom reveal its hidden structure, and discover why a wall is not always the barrier it appears to be. Start with a machine that does one thing. It fires electrons, one at a time, into a dark chamber. On the far wall sits a detector sensitive enough to register the arrival of a single electron as a single point of light. Between the gun and the wall stands a barrier with two narrow openings. That is the whole apparatus. There is nothing hidden in it, nothing exotic, nothing that requires 100 years of theory to describe. Two slits, one gun, one screen. Now we slow the gun down. We turn the current so low that electrons leave the filament like drips from a faucet almost closed, one every few seconds. An electron in that chamber travels the whole distance in something under a billionth of a second. So when one leaves the gun, the previous electron has already been absorbed by the screen for several seconds. The chamber is empty. Whatever happens to an electron in there happens to it alone, with no other electron anywhere in the machine to push it, pull it, or interfere with it in any ordinary sense. Akira Tonomura and his colleagues ran exactly this experiment in 1989, filming the screen for 20 minutes. The first electron arrives, one dot. Somewhere on the screen, no pattern, nothing to learn from it. The second arrives somewhere else. The 10th, the 40th, the 100th. If you stop the film there and look, you see scattered points with no structure at all, spread across the detector like the first drops of rain on dry pavement. I have watched that footage more than once, and the honest thing to say about the first minute is that it looks like failure. It looks like noise. It looks like an experiment that is not going to show you anything. Keep the gun running. Around 1,000 dots, something starts to happen that no one who has not seen it quite believes on first description. The random points are not random. They have been avoiding certain places on the screen. Bands begin to darken where dots keep landing, and between them, stripes where almost nothing has landed at all. By 50,000 electrons, the screen carries clean, evenly spaced fringes, bright and dark, marching across the detector. Those fringes are what water makes when it passes through two gaps in a seawall and the two spreading ripples meet. Crest meets crest. The water piles higher. Crest meets trough. The water flattens to nothing. The pattern on the wall is the arithmetic of a wave passing through both openings at the same moment. Except that we sent the electrons one at a time. Everything tonight grows out of the tension between two facts that refuse to merge. Every electron arrived at the detector as a compact, localized event. One point, full charge, full mass, one click, in one place. Nothing smeared, nothing partial. And yet the places those points were allowed to land were governed by a pattern that requires something to have gone through both slits. Maybe the electrons are interfering with each other. Maybe a stream of them, jostling, produces the stripes the way a crowd produces a pattern of footprints. The low current kills that idea. With one electron in flight at a time and seconds of empty chamber between them, there is no crowd. Tonomura's team could count the arrivals individually. Each electron sees an empty machine. Maybe the electron is not really a particle at all. Maybe it is a small cloud of stuff, and half the cloud goes through the left slit, while the other half goes through the right, and the two halves recombine on the far side. That would explain the fringes beautifully. It also fails the moment you look at the screen, because the screen never records half an electron. It records one whole indivisible charge at one location every time. Nobody has ever measured a fraction of an electron arriving anywhere. If the electrons split, we would expect two smaller flashes, or one weak flash. We get one full flash, always. Perhaps each electron does pass through exactly one slit, and something about the presence of the second slit alters its path on the way, some subtle field, some pressure from the metal edge. That would preserve the particle and explain the pattern together, and physicists took it seriously. There is a clean way to test it. Put a detector at one slit. Do not block anything. Simply watch which slit each electron passes through, then let it continue to the screen. The moment you can tell which slit, the stripes disappear. Not weaken, disappear. What replaces them is exactly the pattern you would draw for ordinary bullets fired at a wall with two holes. A smooth mound of hits behind the left opening, a smooth mound behind the right, and their simple sum in between. Turn the witch slit detector off, and the fringes come back. Turn it on, they go. Nothing about the barrier changed. Nothing about the electrons changed. Only our knowledge of the route changed, and the pattern on the wall changed with it. Something has quietly broken in the word particle. A particle, in the language you and I inherited from the 18th century, is a thing that has a position and follows a path. When it reaches a fork, it takes one branch. Asking which branch is a legitimate question with a definite answer even if nobody bothers to check. The double slit tells us that for the electron, asking is not a neutral act, and the answer does not exist quietly in the background waiting to be read. When no one asks, the electron behaves as though both routes contributed. When someone asks, one route answers, and the contribution of the other vanishes from the pattern. The particle survives as a description of arrival. It fails as a description of travel. To see an electron, you must interact with it, bounce a photon off it, and the photon delivers a kick. Maybe the kick smears the fringes away, and the whole mystery reduces to a clumsy measurement. Physicists chased that answer for decades, and it does not hold. Experiments have been built where the path information is gathered by methods that transfer a momentum kick hundreds of times too small to blur the stripes. The stripes still vanish. Other experiments store the path information without ever reading it, then erase it before the electron lands, and the stripes return, undisturbed, from a kick that was never undone. The fringes track one quantity, and it is not force. They track whether the route is knowable. A physics in which knowability changes the outcome of a measurement is not a physics anyone was looking for. The stripes have a spacing. You can put a ruler on them. Change the voltage on the electron gun, speed the electrons up, and the stripes squeeze closer together. Slow the electrons down, and the stripes spread apart. The relationship is not vague. It is sharp, repeatable, and quantitative. The faster the electron, the shorter the effective wavelength of whatever is doing the interfering. Any wave passing through two slits produces fringes whose spacing depends on one number, the wavelength, together with the geometry of the slits. Measure the fringe spacing and the geometry, and you can solve for the wavelength. Physicists did that with electrons. They found that the wavelength shrank in exact proportion as the momentum of the electron grew. Double the momentum, halve the wavelength. A thing we had called a particle for 30 years arrives with a wavelength attached to it, and that wavelength is set by nothing except how fast the thing is moving and how heavy it is. That is not a metaphor about the electron behaving in a wave-like manner. That is a number, in meters, that you can compute before the experiment and confirm after it. And it did not come from theory first. The wavelength of the electron was measured in a laboratory before anyone had an equation capable of explaining where such a wave comes from, what it is made of, or what it is doing between the gun and the screen. We have a number now, and numbers are foundations. Something travels with the electron, spreads through both openings, carries a wavelength tied to the electron's momentum, and decides where the electron is allowed to land without ever deciding where it will land. Nothing in the physics of 1899 has a place for that object. So, if the electron carries a wave, and we can already measure its wavelength with a ruler and a little geometry, what number in nature sets the exchange rate between a wavelength and a momentum? The number we are looking for was found by a man who did not want it. In the autumn of 1900, Max Planck was trying to fix a formula, not to start a revolution. The problem in front of him was heat and light coming off a hot object, a furnace wall, a glowing filament, a lump of iron pulled from a forge. Classical physics, applied without flinching to that glow, predicted that the object should pour out infinite energy at short wavelengths. Every furnace should have been a fatal source of ultraviolet. Bakers were not dying. Planck patched the mathematics with an assumption he described, for years afterward, as a move made out of desperation. He supposed that the tiny oscillators in the wall of the furnace could not absorb or release energy in whatever amount they pleased. They could only trade energy in discrete lumps, and the size of a lump was fixed by the frequency of the oscillation. Energy equals a constant times frequency. E equals h times f. With that single restriction, the infinity vanished, and the formula matched every measured curve across every temperature anyone had ever put a thermometer to. He believed the lumps were an accounting trick, a property of the wall rather than of the light. For 5 years, the idea sat there, correct and unexplained, a locked door with no one interested in the key. The constant h in the units physicists use is about 6.6 times 10 to the minus 34th. Numbers that small stop meaning anything as words, so hold it against something you can see. Lift an apple from a table to your mouth. The energy that takes is roughly 1 joule. If you asked how many of Planck's lumps of visible green light make up that 1 joule, the answer is around 3 billion billion. 3 billion billion. If each lump were a single grain of sand, the pile would bury the state of Rhode Island. That is why the graininess of energy stayed hidden for 2 centuries of careful experiment. We were never counting grains. We were weighing beaches. Albert Einstein took the door off its hinges in 1905, and he did it with the least glamorous experiment in the building. Shine light on a clean metal surface and electrons come off. That much was known. The behavior of those electrons was not merely unexplained. It was insulting to the wave theory of light, which was otherwise the most successful piece of physics of the 19th century. A wave carries energy spread across its front, and it delivers that energy continuously. Turn a bright lamp on a metal plate, and the electrons should soak up energy like a sponge in a puddle, slowly, until they have enough to break free. Dim the lamp, and they should take longer to fill. Brighten it, and they should escape sooner, and carrying more speed. None of that happens. Below a certain frequency, no electrons come off at all, however bright the light, and however long you leave it there. Hours of red light on cesium, nothing. Above that frequency, electrons appear at once, within billionths of a second of the light arriving, even when the beam is so faint it barely registers on a meter. Brightening the light does not give the electrons more speed. It gives you more electrons, each with the same energy as before. Raise the frequency, and only then does each escaping electron carry more energy, and it does so along a perfectly straight line when you plot energy against frequency. Einstein read that straight line for what it is. Light arrives in units. Each unit carries energy equal to h times its frequency, and one unit hits one electron. If a single unit does not carry enough energy to pay the electron's escape cost from the metal, no amount of piling on more units helps, because the electron is not saving up. It is being struck once. The threshold frequency is the price of the ticket. The brightness is the number of tickets sold. Robert Millikan spent 10 years trying to prove Einstein wrong about this. He was an outstanding experimentalist, and he thought the light quantum idea was reckless. What he built was the most precise test of the photoelectric equation anyone had made, and by 1916, his own data had confirmed it line for line. The slope of that straight line, measured in his laboratory with voltages and lamps, gave a value for Planck's constant that agreed with the value Planck had pulled out of furnace radiation 16 years earlier. He had spent a decade building the instrument that defeated him, and he published the result anyway. Two completely unrelated corners of physics, hot iron and cold metal plates, reporting the same number to 3 decimal places. That is what a real constant of nature looks like when it shows up. It comes back with the same face in a room where nobody invited it. So light, the textbook wave, is quantized. Each quantum carries energy h times f, and by the relativity, Einstein had published the same year, a thing that moves at light speed with energy E carries momentum equal to E divided by c. Substitute. Momentum equals h times f divided by c. And since frequency times wavelength equals speed for any wave, f over c is simply 1 over the wavelength. Momentum equals h divided by wavelength. P equals h over lambda. Light, which everyone knew was a wave, has momentum, which everyone knew belonged to particles. The bridge was built from the wave side, and hardly anyone noticed it went both directions. In 1923, a French graduate student named Louis de Broglie noticed. His doctoral thesis contained an argument so short it embarrassed his examiners, who could not decide whether it was empty or the most important thing they had read that year. If a wave can carry momentum, and momentum equals h over wavelength, then perhaps the equation should be read backwards. Take an electron. It has momentum. Solve for a wavelength. Lambda equals h divided by p. Not a metaphorical wavelength, a number, in meters, belonging to a lump of matter. De Broglie could not say what was waving. He could only say that the arithmetic of light seemed too clean to belong to light alone. Run the number, and you see why nobody had tripped over this before. A baseball leaving a pitcher's hand has a de Broglie wavelength around 10 to the minus 34 meters. A proton is 10 to the minus 15 meters across, and the baseball's wavelength is 100 billion times smaller than a proton. There is no slit that narrow, no crystal with gaps that fine, no way in this universe or any laboratory to make a baseball diffract. Now, take an electron accelerated across a modest voltage, the kind of voltage in an old television tube. Its momentum is small because its mass is small, and its wavelength comes out around 1/10 of a nanometer. That is the spacing between atoms in a metal crystal. Nature had already built the diffraction grating. It was sitting in every piece of nickel in every drawer of every laboratory in the world. Clinton Davison and Lester Germer found it by accident in 1927. A bottle of liquid air exploded in their laboratory. The vacuum broke. Their nickel target oxidized, and while baking it clean, they accidentally grew it into large crystals. When they resumed firing electrons at it, the electrons no longer scattered in the smooth spray they had recorded before. They came off in sharp preferred directions, at specific angles, the way X-rays come off a crystal. Feed the angles into the same geometry crystallographers had been using for a decade, and you extract a wavelength. Compare it against h divided by the momentum of the electrons, which they knew precisely from the accelerating voltage. The two agreed. An accident with a broken vacuum measured the wavelength of matter. So we have two equations, and neither of them is a hypothesis anymore. E equals hf, confirmed independently from furnace curves and photocells. P equals h over lambda, confirmed by electrons bouncing off nickel, and, within a year, off gold foil and off crystals of everything else physicists could get their hands on. Physicists usually write both in terms of h divided by 2 pi, called h bar, since waves are more naturally described by angular frequency omega and by wave number k rather than by f and lambda. In that dress, the two equations read E equals h bar omega and P equals h bar k. Two sentences. One, constant. Energy is tied to how fast the wave oscillates in time, momentum to how tightly it oscillates in space. Every piece of matter you can name comes with a wave whose oscillation in time is fixed by its energy, and whose oscillation in space is fixed by its momentum. We know the exchange rate. We do not yet have the wave. What would the simplest thing that oscillates in space and in time have to look like, written down, before nature is allowed to say no? Nature has told us two things about the wave that travels with a particle, and it has told us nothing else. The wave repeats in time at a rate set by the particle's energy. It repeats in space at a rate set by the particle's momentum. Both of those facts were pulled out of laboratories, not out of anyone's head. So we do the only reasonable thing available to us. We write down the simplest mathematical object that repeats in space and repeats in time, and we see what it costs us. Everybody's first guess is a cosine. Draw the curve you saw in a physics classroom, the smooth hills and valleys, and let the whole shape slide to the right as time runs forward. Cosine of kx minus omega t. The letter k sets how many hills fit in a meter, and it equals 2 pi divided by the wavelength. The letter omega sets how fast the shape oscillates in place, and it equals 2 pi times the frequency. Those two letters are the same two knobs Louis de Broglie handed us, dressed in the notation waves prefer. Energy sits in omega. Momentum sits in k. The cosine already contains both. And the cosine fails for a reason that has nothing to do with taste. Look at what the curve does at the places where it crosses zero. Twice in every cycle, at evenly spaced points along its length, the wave has no height at all. Between two hills there is a spot where the electron's wave amounts to precisely nothing. Now remember what we are describing. A free electron, flying through empty space with a definite momentum, unbothered, not confined by anything. Nothing in that situation singles out one location over another. Empty space has no landmarks. Yet, the cosine has painted a permanent lattice of dead points across the vacuum, fixed in place, each one a location where the electron's wave simply is not. A description of the free electron should read the same at every point along its motion. The cosine does not. It picks out addresses in a universe with no addresses. Someone will push back. The zeros of a traveling cosine do not stand still. The whole shape moves, so a point that is a zero now becomes a crest a moment later. Over any stretch of time, every location gets its turn. That is fair, and it is not enough. The wave still stutters. At the instant a crest passes through zero, the entire structure that is supposed to describe the electron flickers to nothing everywhere along a whole surface. Something that vanishes and reappears twice per cycle is a poor candidate for describing a thing that never stops existing. There is a second failure, and it is the one that will decide everything. We want to get the energy and the momentum back out of this wave once we have written it down. Those two numbers are buried in omega and k, and the tool that pulls out omega and k is the derivative. Since taking a derivative asks a function how fast it is changing. Take the time derivative of cosine, and you get minus sine times omega. The omega comes out, and the cosine turns into a sine. The function has changed identity. Ask again, and it changes back with a sign flip. Every question we ask this wave, it answers as a different function than the one we asked. We can never write a clean statement of the form. When I differentiate this wave, I recover the wave itself multiplied by its energy. So we go looking for a function that survives differentiation. One that comes back as itself, scaled by a number. Mathematics has exactly one family that does this, and every high school algebra student has met it without being told what it is for. The exponential. The derivative of e to the ax is a times e to the ax. The function returns unharmed, carrying the constant a out front like a receipt. That property is not a convenience. It is the reason exponentials appear everywhere. A rate of change is proportional to the amount present in radioactive decay, in compound interest, in the cooling of a cup of tea. The trouble is that exponentials do not oscillate. They grow without limit, or they die away to nothing, and neither behavior describes a wave that keeps repeating forever with the same size. Unless the constant a is imaginary. The imaginary unit will run the rest of this equation and most of the physics that came after it. The letter I is defined by one property. Multiply I by itself, and you get -1. No ordinary number does that, since a positive times a positive is positive, and a negative times a negative is also positive. So I live somewhere the number line does not reach. Put it in a place. Draw the familiar number line running left and right, then draw a second axis running up and down, and let I be the point 1 unit above 0. Now every number is a point on a plane, and every point on a plane can be described two ways: by its coordinates, or by an arrow from the origin with a length and an angle. Multiplying by I does something specific to that arrow. It rotates it a quarter turn counterclockwise and leaves its length untouched. 1 rotated becomes I rotated becomes -1, which is exactly the defining property, since 2 quarter turns face you backwards. Multiplication by I is not a strange operation on a strange number. It is the instruction to turn 90 degrees. Now ask what function has the property that its rate of change is always I times itself. The answer is e to the I theta, and you can read what it must do from the geometry alone. Its rate of change equals its current value rotated a quarter turn. An arrow whose velocity is always perpendicular to the arrow itself cannot get longer and cannot get shorter, since nothing is pushing along its length. It can only swing. An arrow of fixed length, turning at a steady rate, is a point moving around a circle, which is precisely what Leonhard Euler wrote down. E to the I theta equals cosine theta plus I times sine theta. The horizontal shadow of the turning arrow traces a cosine. The vertical shadow traces a sine. The arrow itself does neither. It simply turns, at constant length, forever. So write the wave the only way it will let itself be written. Psi of x and t equals a times e to the I times the quantity kx minus omega t. That object is not the curve from the physics classroom. At every point in space there sits a little arrow in the complex plane. As time passes, every one of those arrows rotates at the same rate, omega, set by the particle's energy. At any frozen instant, the arrows do not all point the same way. Walk along the x-axis and their angles wind steadily forward at rate k, set by the particle's momentum. The whole structure is a corkscrew of arrows, spinning in time, twisting in space. Every arrow has the same length, a, at every point, at every moment. The wave never flickers. It never has a zero. It never picks out an address in empty space. The free electron looks identical everywhere along its path, which is what emptiness demands. The oscillation is still there, entirely, but it has moved from the length of the arrow into its angle. That angle has a name we will need. Physicists call it the phase. Watch a crest travel, if you insist on a crest. Follow a point where the arrows all aim in some chosen direction, and that point slides forward at speed omega divided by k. Feed in the two equations from the laboratory. Omega equals energy over h bar, k equals momentum over h bar, and that speed comes out as energy divided by momentum. For a slow particle that is 1/2 of its ordinary speed, a discrepancy that will matter later and that nobody in 1925 found comfortable. Engineers use complex numbers for alternating current every day, and at the end of every calculation they throw away the imaginary part and keep what is real, because the current in the wire is a real number of amperes. Perhaps this psi is the same convenience. Perhaps the I is scaffolding to be discarded once the building stands. That is what everyone assumed. It is not what happened. The I in this wave cannot be removed at the end, and the reason it cannot is stranger than the reason it appeared. We have a wave now, one arrow long, turning at rate omega and winding at rate k. We have a tool that reads rates of change, and a wave built specifically to survive it. What comes back when we finally point that tool at this corkscrew and ask it how fast it is turning? Point the derivative at the wave and see what falls out. We built psi to equal a times e to the I times kx minus omega t. Ask how it changes as time passes, holding position fixed. The exponential comes back unharmed, and out front sits the constant that was multiplying t inside the exponent. That constant is minus I omega. So the time derivative of psi equals minus I omega times psi. The wave has handed us its own frequency and handed back a perfect copy of itself along with it. Nothing about that is yet physics. Omega is a number about wiggling. We want energy. Laboratory measurement gave us the exchange rate. Energy equals h bar times omega, so multiply both sides by I h bar. On the left, we now have I h bar times the time derivative of psi. On the right, minus I times I is 1, and h bar omega is E. I h bar times the rate of change of psi in time equals E times psi. That line has a shape that will repeat for the rest of the night. On one side, an instruction performed on the wave. On the other side, the same wave, unchanged, multiplied by a plain number. The instruction did not damage psi. It interrogated it, and psi answered with a number, and that number is the energy of the particle. Do the same thing along space. Ask how psi changes as you step along x, holding time fixed. The exponential survives again, and this time the constant out front is ik. The space derivative of psi equals ik times psi. Momentum equals h bar k, so multiply by minus I h bar. Minus I times I is 1 again. Minus I h bar times the rate of change of psi in space equals p times psi. Two sentences with the same architecture. Something is done to the wave. The wave comes back untouched, and a physical quantity appears out front as a bare number. Physicists gave that arrangement a name in the 1920s, and the name has never left. The instruction is an operator. The special function that survives it is an eigenfunction. The number that falls out is an eigenvalue. Strip the German off, and what remains is simple. An operator is a question. An eigenfunction is a wave that has a definite answer to that question. The eigenvalue is the answer. So energy has become an instruction. Take the time derivative and multiply by IH bar. Momentum has become an instruction. Take the space derivative and multiply by minus IH bar. In the physics we grew up with, energy and momentum were numbers you carried around, properties stapled to an object like its color. Here they are things you do to a wave. This is circular. We chose psi to be an exponential precisely because exponentials survive differentiation. Then we differentiated and pretended to be surprised. Of course, omega came out. We put it in. It is not circular, and the reason lives one step back. The exponential was not chosen for the convenience of the derivative. It was forced on us by two facts about free particles, that their wave cannot have fixed dead points scattered through empty space, and that it cannot flicker out of existence twice per cycle. Only the complex exponential threads both needles. And the claim that omega means energy is not something we invented on paper. It came out of a furnace in 1900 and out of a metal plate in 1905. Given those two imports, one from mathematics and one from measurement, the operator forms are not a choice anyone made. They are what remains after both constraints are satisfied. That is the difference between a definition and a discovery. A definition can be swapped for another. This one cannot be swapped without breaking either the vacuum or the laboratory. Now push the derivative one step further along space. Differentiate psi twice. Each pass hands you a factor of ik. So two passes hand you ik times ik, which is minus k squared. The second space derivative of psi equals minus k squared times psi. Multiply through by minus h bar squared. The minus signs cancel, and h bar k appears twice, so what stands in front of psi is p squared. Minus h bar squared times the second space derivative of psi equals p squared times psi. Kinetic energy for a slow particle is p squared over 2m. Divide the whole line by 2m and the instruction for kinetic energy assembles itself. Minus h bar squared over 2m times the second derivative in space. The curvature of the wave has become the kinetic energy of the particle. The sharper the wave bends, the shorter its wavelength, the larger its momentum, the more kinetic energy it carries. A gently rolling wave belongs to a slow particle. A tightly wound one belongs to a fast particle. That is not an image laid over the mathematics. It is the mathematics read out loud. There is a consequence of this that took a decade to appreciate, and once you see it, you cannot look at classical physics the same way. Momentum is now an instruction involving a derivative. Position is also an instruction, and a boring one, since asking a wave where it is amounts to multiplying it by x. Two instructions, one after the other, Instructions have an order. Multiply psi by x, then differentiate, or differentiate first, then multiply by x. Those are not the same operation, and any calculus student knows why. Differentiating a product of x and psi produces two terms, since x itself changes as you move along x. The two orderings do not cancel. What survives the subtraction is a constant, and the constant is IH bar. Position times momentum minus momentum times position does not vanish. In classical mechanics, that difference is exactly zero, because a number times a number is the same in either order and nobody ever thought to ask. Here the difference is a fixed, tiny, universal amount. Everything you have heard about not being able to pin down a particle's position and its momentum at the same time is sitting inside that one line, waiting. No philosophy required. Two instructions refuse to commute, and the size of their disagreement is Planck's constant. Watch what this does to the idea of a property. Our plane wave has a perfectly definite momentum because when we ask it the momentum question, one clean number comes back. It has no definite position at all because it looks the same at every point in space. Now imagine a wave shaped like a narrow bump sitting at one place. Ask it the momentum question. Differentiate a bump and you do not get the same bump back multiplied by a number. You get something else entirely. The bump has no answer to give, not a hidden answer, not an answer we are too clumsy to read. The mathematics has no number to hand over because the wave is not an eigenfunction of that question. A localized particle does not have a momentum that we fail to know. It has a wave that fails to have one. The bare time derivative of psi returned minus I omega, an imaginary number. Energy measured in a laboratory is never imaginary. Multiplying by IH bar rotates that answer back onto the real number line, where joules live. Same story along space. Differentiation alone gives IK, and the minus IH bar out front turns it into a real momentum. The imaginary unit enters the wave and leaves through the operator, and the number that reaches the meter is real. A theory built on a number that does not exist returns only numbers that do. Everything in ordinary life trains us to believe that a thing has its properties whether or not anyone checks. The mathematics we just built does not contain a place to store a property that has no definite value. It contains a wave and questions you may ask the wave, and only some questions have answers. Take stock of the tools on the table. Energy is IH bar times the time derivative. Momentum is minus IH bar times the space derivative. Kinetic energy is minus h bar squared over 2m times the second space derivative. Every one of them extracted from a single wave that we were forced to write. We are holding three translations from the old physics into the new. What we do not have is a single true sentence connecting energy to momentum, one that held before quantum mechanics and will still be standing after it. Where in 300 years of mechanics is the one statement about a moving particle that nobody, not Newton and not Einstein, was ever able to break? A ball rolls up a hill and slows down. It rolls back and speeds up again, and if the grass takes nothing from it, it returns to your hand at the speed you threw it. Nothing about that is quantum. Nothing about it is even modern. Yet inside that ordinary sentence sits the last piece we need, and it is the only piece we will not derive tonight, because nobody derives it. It is the thing everything else is derived from. Energy is conserved. Not created, not destroyed, only moved between two accounts. The account called motion and the account called position. Motion carries kinetic energy. For a particle moving slowly compared to light, that is 1/2 mv squared. And since momentum p equals mv, the same thing written in the currency we now prefer is p squared divided by 2m. Position carries potential energy, and we call it v of x, because how much of it a particle holds depends on where the particle is standing. High on the hill, the ball owns a great deal of v and almost no motion. At the bottom, all of it has moved into the other account. The sum never changes. Kinetic plus potential equals E, a single number belonging to that particle, fixed for as long as nothing outside interferes. P squared over 2m plus v of x equals E. Take v of x seriously for a moment, because it is doing more work than its plain notation suggests. V is not a force. It is a landscape. Give me the shape of V along a line and I can hand you back the force at every point, since the force is how steeply V drops. Steep slope, strong push. Flat ground, no push at all. An electron near a proton sits in a V that falls away like a funnel, deeper and deeper as it approaches. A particle in a hollow container sits in a V that is flat inside and rises like a cliff at the walls. Every physical situation in this entire subject is a choice of V, and only a choice of V. Change the landscape, change the physics, and change nothing else. Gottfried Leibniz argued for something like it in the 1680s and was ridiculed. Émile du Châtelet showed in the 1740s that the quantity that survives collisions goes as the square of the speed, not the speed itself, which is why the 2 in 2m is there and not somewhere else. It took another century for James Prescott Joule to prove that heat belonged in the same ledger by measuring how much a paddle wheel warmed a tub of water. And in 1918, Emmy Noether proved something that still stops me when I say it out loud. Energy is conserved because the laws of physics do not care what time it is. Run your experiment today, or run it in 1,000 years. The rules are identical, and out of that indifference alone, mathematically, conservation of energy follows. It is not an observed accident. It is what a universe with no preferred moment is obliged to do. So, this one sentence has a foundation deeper than Newton, and it survived the arrival of relativity, of thermodynamics, of chemistry, of everything. Erwin Schrödinger, sitting in a rented villa in the Swiss Alps over the Christmas holiday of 1925, had no intention of abandoning it. He wanted a wave equation for matter. He had de Broglie's thesis, which he had read only because Peter Debye had asked him, in a seminar, what the waves in it were supposed to obey. Nobody had an answer. Debye's question was more or less an idle one. Schrödinger went away and came back with the answer 6 weeks later. His first attempt was not the equation we are building. He tried the relativistic version, using the full energy-momentum relation from Einstein instead of the slow particle approximation. It is a natural first move for a man who had spent years on relativity. He solved it for the hydrogen atom, compared it against the measured spectrum, and the fine details came out wrong. He set it aside, discouraged, and retreated to the ordinary, unglamorous, slow particle statement about energy that a 15-year-old could recite. That version worked. The relativistic one he abandoned was rediscovered by others and turned out to be correct for particles without spin, and the reason it failed for hydrogen is that the electron has a spin nobody had put into the mathematics. He was not wrong. He was early, and he was missing an ingredient that would not exist for 2 more years. Energy is IH bar times the time derivative. Momentum is minus IH bar times the space derivative. Kinetic energy, being P squared over 2m, is minus h bar squared over 2m times the second space derivative. And potential energy is the easiest of all. Asking a wave how much potential energy it has at a point means multiplying it, right there, by v of x. No derivative, no I, nothing. Just the landscape scaling the wave, point by point. That difference between the two kinds of instruction carries a physical statement inside it. Kinetic energy asks the wave a question that cannot be answered at a single point, since a derivative needs the neighbors on either side to know how fast something is changing. Potential energy asks a question that needs no neighbors at all. The landscape at this point times the wave at this point, and nothing else enters. Motion is a property of the wave's shape across a region. Position energy is a property of where the wave happens to be standing. The equation we are assembling will therefore couple every point to the points beside it, which is the whole reason a disturbance in psi can travel. Take the classical sentence and let every symbol in it stop being a number and become an instruction. Then let both sides of the sentence perform their instructions on psi. Kinetic energy acting on psi plus v of x times psi equals the energy instruction acting on psi. Nothing in mathematics required Schrödinger to promote a classical equation into an operator equation. He guessed. It was an educated, constrained, beautifully narrow guess, and it was still a guess. Physics permits exactly one kind of defense for a guess. You follow it out to a number, and you go look. There is a way to see how narrow the guess was. Feed the free plane wave into the finished statement, with v set to 0, an electron flying through empty space. The energy instruction pulls E out front. The kinetic energy instruction pulls p squared over 2m out front. Both sides come back as psi, multiplied by a number. Cancel psi from both sides, since it is the same wave on each. What remains, standing alone on the page, is E equals p squared over 2m. The classical sentence, returned intact, out of a machine built entirely from operators and imaginary numbers. The translation did not damage the old physics. It contends it. I have never been able to decide which direction that fact points. You can read it as reassurance, the new theory politely reproducing the old one where the old one was tested. Or you can read it the other way. The classical equation had been sitting there since Leibniz, quietly containing the shape of a wave equation, waiting for someone to notice that its symbols were instructions all along. What we have written down so far is only half a sentence, and the half that is missing is the interesting half. With v equal to 0, our finished statement contains no time and no place. It says a free particle has an energy set by its momentum, which everybody knew. Switch v on. Put a hill in front of the electron, or a funnel, or a wall. Now the potential energy varies from point to point, so the equation demands something different from psi in one region than in another. The wave has to bend. It has to change its curvature to keep the accounts balanced, more curvature where the landscape is low, less where the landscape rises. The wave has to respond to the world. So we write the whole thing out, all three instructions in one line, with v of x standing in it as an open slot into which any physical situation in the universe can be dropped. Every symbol in that line has now been earned. 2 of them came from a furnace and a metal plate. 1 came from a corkscrew of arrows we were forced to draw. 1 came from Leibniz and a paddle wheel and a woman in France arguing about squares. What does the sentence look like when they all stand in the same line, and what is it commanding the wave to do? The line goes together in one order and no other. I/h bar times the rate of change of psi in time equals minus h bar squared over 2m times the second rate of change of psi in space plus v of x times psi. One line. Read from left to right. It says that how fast the wave turns at a point is decided by two things and nothing else. How sharply the wave is curving at that point, and how high the landscape stands there. Curvature and altitude. In. Rate of turning. Out. A rule that a point in the wave can obey, knowing only its immediate neighbors and the local value of v. Nothing in this equation reaches across the room. Everything is local, and the whole global behavior of matter is built out of that locality, repeated at every point. Nobody handed us this from above. Watch where each piece came from. The I and the H bar on the left came out of a furnace glowing in 1900 and a metal plate in 1905. Through the statement that energy is H bar times frequency, and through the fact that reading a frequency off a rotating arrow requires a derivative and returns an imaginary number that I cancels. The second derivative on the right came from de Broglie and a broken vacuum flask in a laboratory in New Jersey. Through momentum equals H bar times wave number, applied twice. The 2 meters under it came from Du Châtelet, arguing about squares, in the 1740s. V of x came from a ball on a hill. The only ingredient that was ever a guess is the instruction to let those symbols act on a wave instead of standing as numbers. Everything else was measured. Test the line before trusting it. Take our corkscrew wave, the free electron, and set v to 0. Differentiate once in time and the left side returns E times psi. Differentiate twice in space and the right side returns p squared over 2m times psi. Divide out psi, which appears identically on both sides. E equals p squared over 2m. Whatever else this equation is doing, it is not contradicting the physics that built the world we can see. A free electron obeys the same energy bookkeeping a rolling ball obeys, and the corkscrew was quietly carrying that bookkeeping the entire time. Now count derivatives on each side, because the count is not symmetric, and the asymmetry is the strangest thing on the page. Time appears once. Space appears twice. Compare that against every wave equation written before 1926. A vibrating string, a sound wave, light in a vacuum. All of them have 2 time derivatives and 2 space derivatives in balance, and that balance is why a wave on a string travels at a single fixed speed. This equation is lopsided. The consequence is enormous, and almost nobody points at it. Think about what Isaac Newton needs before he can predict where a planet will be. He needs its position now, and he needs its velocity now. 2 pieces of information. Position alone is not enough, and everyone knows it. 2 identical planets at the same place, moving differently, have different futures. Newton's law has 2 time derivatives in it, so it demands 2 initial facts. Our equation has 1 time derivative. It demands 1 initial fact. Give me psi everywhere at 1 instant, the whole complex wave, every arrow's length and angle, and the equation hands me psi at every instant afterward, forever, with nothing left to specify. No velocity of the wave needs supplying. The wave's rate of change is not an independent fact about it. It is dictated, at every point, by the wave's own shape, which makes this equation completely deterministic. Perfectly, rigidly, boringly deterministic, in exactly the sense Pierre-Simon Laplace meant when he imagined an intelligence that knew the present and could compute the entire future. There is no chance in this line. There is no probability in it. There is nothing random anywhere. I want that on the record now, in the middle of the night, before anybody tells you that quantum mechanics is a theory about randomness. The central equation of quantum mechanics has less randomness in it than the weather. Where the randomness comes from, and why it is not in this line, is a debt we are going to have to pay later, and it is not a small one. Physicists compress the right side into a single symbol and call it H, after William Rowan Hamilton, who reorganized classical mechanics around the total energy of a system a century before any of this. H psi is shorthand for take the curvature term and add the landscape term. With that, the whole of the theory reads as I h bar times the rate of change of psi equals h psi. 4 symbols and a derivative. And H is where every physical situation you will ever meet has to enter. 2 electrons repelling put their repulsion into H. A magnetic field into H. A crystal lattice into H. An atom, a molecule, a transistor, a star's core. All of them are the same equation with a different H. The structure never changes. Only the landscape does. Check the bookkeeping if you like, since a wrong equation usually announces itself in the units. H bar carries units of energy times time, and a rate of change in time cancels the time, leaving energy. On the right, H bar squared over mass, divided by a length squared, also reduces to energy. V of x is an energy by construction. 3 terms, 3 energies, all multiplying psi. The equation is a statement about energy that happens to be written with derivatives. There is a price for the lopsided derivatives, and it shows up the moment you build a wave that is not a plane wave. Ask how fast a given wavelength travels under this equation. Substitute the corkscrew, and you get omega equals h bar k squared over 2m. That is not the relation a string obeys. On a string, omega is proportional to k, so every wavelength travels at the same speed, and a pulse keeps its shape as it moves. Here, omega goes as k squared. Short wavelengths travel faster than long ones. Any localized bump, being a sum of many wavelengths, must therefore come apart as it moves. The fast components run ahead. The slow ones lag. The bump spreads. Put a number on it, because this is one of those places where the number decides whether the theory is describing your world or a footnote. Confine an electron to a region about 1 nanometer across, roughly the width of a strand of DNA. The equation says that bump doubles in width in something near 10 femtoseconds. 10 femtoseconds is to 1 second roughly what 1 second is to 3 million years. An electron cannot stay put. Left alone, its wave floods outward almost immediately, and that flooding is not carelessness on our part. It is the equation. Now do the same for a grain of dust, 1/10 of a millimeter across, weighing a microgram. Same equation, same instruction. The mass in the denominator is now 1 billion times larger, and the spreading time comes out longer than the age of the universe. Nothing changed about the physics. The dust grain obeys precisely the line we wrote. Its wave is spreading right now, on your windowsill, at a rate that will not matter before the stars burn out. There is no boundary in this equation between the quantum world and the ordinary one. There is a mass in a denominator. Every so often I catch myself reading the line again just to check that it is that short. 1 derivative in time. 1 curvature in space. 1 landscape. 1 imaginary unit that refuses to be dismissed. No forces appear anywhere in it, though forces come out of it. No trajectories appear in it, though the paths of every particle in a television tube come out of it. No probabilities appear in it, though every probability in the physical sciences comes out of it. And there is a hole in the middle of the page. The line tells us with total precision how psi evolves. It never once says what psi is. Look for the definition. There is no definition. Psi entered as the simplest thing that could oscillate in space and time with a frequency set by energy, and it has been promoted, silently, to the object that carries everything the theory knows about a particle. The equation treats it as sacred and never introduces it. Schrödinger himself believed that winter, that psi was a real physical vibration, a smear of electric charge spread through space. He would spend the rest of his life unhappy about the meaning the theory settled on. If psi is not the electron spread thin, and it is not a number we can measure with any instrument ever built, then what does a complex arrow at every point in space have to do with finding an electron somewhere? Schrödinger had an answer ready, and for a few months in 1926, it was the only answer on offer. Psi is the electron, spread out. Multiply the size of the wave at a point by the electron's charge, and you get how much charge sits there. The electron is not a dot at all. It is a cloud, thick where psi is large, thin where psi is small, and the whole thing glides through space obeying his equation. No paradox, no mystery, no dice. A wave that people had mistaken for a particle because they had only ever seen it hit things hard. The idea is beautiful, and it is dead within a year, and the way it dies teaches you what psi is by telling you what it cannot be. The first wound comes straight from the equation. A localized wave spreads. We measured how fast, and for an electron confined to the width of a strand of DNA, the wave floods outward in 10 femtoseconds. Fire that electron across a laboratory, a distance it crosses in a few nanoseconds, and by the time it arrives, its wave is enormous, meters across, thinly smeared over the whole far wall. If psi were a cloud of charge, the detector should register a faint whisper of charge everywhere along that wall, simultaneously. Every detector ever built records the opposite. One full electron charge at one point, and nothing anywhere else in the same instant. The cloud arrives spread. The click arrives whole. Schrödinger tried to rescue it. Perhaps the cloud collapses in on itself at the moment of arrival, pulled together by some non-linear effect. His equation was too simple to contain. That rescue requires the collapse to happen faster than light, across the whole width of the spread wave, so that the charge 2 meters to the left knows instantly not to arrive. No equation he could write did that. No equation anyone has written since does that. The second wound is worse, and it is the one that ends the argument permanently. Write the equation for 2 electrons instead of 1. The wave now depends on where the first electron is and where the second electron is at once. 3 coordinates for one, 3 for the other. Psi becomes a function of 6 numbers. A cloud of charge lives in the 3 dimensions of the room. This object does not. It lives in a 6-dimensional space that has no room, no walls, no floor, and no location. 3 electrons, 9 dimensions. A carbon atom's 6 electrons, 18. Nothing physical is waving in 18 dimensions in your kitchen. Whatever psi is, it is not a substance distributed through the space you are lying in. It is a bookkeeping object defined over the possible arrangements of things. Psi is not a thing in space. It took physicists a year to say that sentence and the rest of the century to stop flinching at it. Max Born was working on a different problem entirely, in the summer of 1926, at Göttingen. He was calculating what happens when a beam of particles scatters off a target, and he needed to know what the outgoing wave was telling him. The paper he wrote contains the answer in a footnote, added while the paper was already in press, because his first attempt in the main text had been slightly wrong. The size of the wave at a point does not give the amount of electron there. Its squared magnitude gives the probability of finding the whole electron there. Squared magnitude, not psi. The length of the arrow times itself. Written down. The probability of finding the particle in a small stretch of space around x is psi star times psi, times the width of that stretch. Psi star is the arrow with its angle reversed, and multiplying the two kills every trace of angle and leaves a plain positive number, the square of the arrow's length. The squaring is not a stylistic choice. 3 separate demands force it. Psi is complex, and no experiment has ever measured a complex number. So whatever we hand to the laboratory must be real. A probability cannot be negative, and psi swings negative twice per cycle. And a probability must not depend on where you happen to start your clock, but psi's angle depends entirely on that. Squaring the magnitude solves all 3 at once, and it is the only simple operation that does. The arrow's length carries what you can know. The arrow's angle carries nothing you can measure, and everything the wave needs in order to evolve. Something is lost in that squaring. 2 waves whose arrows have the same length everywhere but different angles are indistinguishable to any single measurement of position. They are utterly different objects to the equation, and they will do different things a moment from now. The phase is invisible, and it is not idle. An electron whose arrows have been turned, all together, by a uniform angle, behaves identically. Turn them by an angle that varies from place to place, and you have changed the momentum, and the electron flies off somewhere else. What you cannot see about the wave is what determines where it goes. Add the requirement that the electron exists. Sum the probability over every point in space, and the total has to be 1, since the particle is somewhere. That is the normalization condition, and it fixes the constant A we left hanging in the corkscrew and never chose. The equation determines the shape of psi. The demand that the particle be somewhere determines its overall size. Units fall out of it too, and they are peculiar. If psi squared is a probability per unit length, then psi carries units of 1 over the square root of a length. There is no instrument on Earth calibrated in inverse square roots of meters. Psi is the square root of something measurable, and square roots of probabilities are not things. They are what you must have in order for probabilities to interfere. Now the equation can do arithmetic for you. If the probability of finding the particle at each point is psi squared, then the average position, over many repetitions of the identical experiment, is the sum of each position weighted by its probability. Physicists write it as an integral of x times psi squared, and they call it the expectation value of x. That name misleads people every year. It is not what you expect to see. Fire 10,000 identical electrons through an identical apparatus, record where each one lands, average the 10,000 numbers, and you get the expectation value. Any single electron may land nowhere near it. The average position of a wave with 2 humps can sit in the empty valley between them, at a place the electron never once arrives. Every quantity in this theory works that way. The equation predicts distribution. Experiments deliver events. Which is the whole trouble, stated as plainly as I know how to state it. The wave evolves without a shred of chance in it. Feed in psi now. Get psi later. Exactly. Forever. And then one electron strikes one phosphor grain, and the theory offers no mechanism whatsoever for why that grain and not the one beside it. Born's rule tells you the odds. It does not tell you the cause, and it does not claim to. It was appended to the theory as a separate statement, in a footnote, and a century of work has not succeeded in deriving it from the equation it accompanies. Albert Einstein never accepted it, and his objection was not squeamishness about randomness. He thought a theory that predicts only averages is a theory that has not finished. That statistical mechanics also predicts only averages, and nobody minds, because underneath it sit molecules with definite positions. He wanted the molecules. He spent 30 years looking for what sits underneath psi. Nobody has found it, and there are now good arguments that nothing of the kind can be found without giving up something people value more. Schrödinger, for his part, regarded Born's reading of his own equation as a defeat, and said so for 30 years. He built the most successful predictive instrument in the history of science and disliked what it predicted. There is a kind of loneliness in that which I do not think gets said often enough about him. So psi is a complex arrow at every arrangement of the world, whose length squared gives a probability, and whose angle gives nothing measurable at all. The total probability, summed over everywhere, equals 1, and the particle exists. But probability that adds to 1 now has to add to 1 an hour from now, and nothing we have written down so far promises that psi will keep it that way. Cross out the I. It sits there on the left of the equation, an ornament from a branch of mathematics invented to solve cubic polynomials in the 1500s, and a reasonable person wants to know what a number with no place on the number line is doing in a law of nature. So delete it and see what breaks. Take the free case, no landscape, v equal to 0. Without the I, the equation reads that the rate of change of psi in time equals a positive constant times its curvature in space. That equation has a name, and it is not new. It is the heat equation, written by Joseph Fourier in 1822, and it describes how warmth crawls through an iron bar. Every physicist recognizes it on sight. Wherever the temperature curves upward, the spot warms. Wherever it curves downward, the spot cools. Bumps flatten. Dips fill in. Everything trends toward bland, uniform sameness. Feed our corkscrew into it and the arithmetic is brutal. The solution comes out as the same spatial wave multiplied by e to the minus a positive number times t. Not a rotation, a decay. The arrows do not turn. They shrink. Every arrow in the wave gets shorter as the seconds pass, and since the length squared is the probability of finding the electron, the total probability of finding the electron anywhere at all falls steadily toward 0. Wait long enough and the electron is not somewhere else. It is nowhere. Matter would leak out of existence at a rate set by its own wavelength, and short wavelength matter, the tightly wound kind, would vanish fastest of all. Run the number for an electron whose wavelength is 1 nanometer, about 3 atoms wide. In that crossed-out equation, its wave falls to nothing in under a femtosecond. A femtosecond is to a single second what a single second is to about 30 million years. Every atom in your body would have emptied itself before the first cell of you ever formed. That is what one crossed-out symbol costs. Not elegance, existence. The heat equation destroys more than that. It has an arrow built into it. Run it forward, and a hot spot spreads into a smooth, warm region, and the memory of exactly where the heat began is gone forever, mathematically unrecoverable. Run the film backward, and the equation breaks, since a smooth region will not spontaneously gather itself into a spike. Schrödinger's equation, with the I intact, runs backward as easily as forward. Reverse the sign of time and take the mirror image of every arrow, and the wave retraces its own history exactly. Nothing is forgotten. Nothing is smoothed away. The information in psi now is precisely the information in psi a billion years from now, rearranged. One symbol separates a universe that forgets from a universe that does not. So the I is doing something. Naming it requires one honest piece of calculus, and it is the most satisfying half-page in this entire subject. So we take it slowly. Probability at a point is psi star times psi, the arrow's length squared. Ask how fast that quantity changes with time. Both factors are changing, so the rate of change of the product has two terms, one where psi changes and one where psi star changes. Schrödinger's equation tells us how psi changes. Flip every I to a minus I, and it tells us how psi star changes, since the complex conjugate of an equation is still a true equation. Substitute both, and something specific happens to the potential energy term. V times psi star psi appears once with an I out front and once with a minus I out front. The two cancel exactly, and the landscape drops out of the calculation entirely. Potential energy cannot create or destroy probability. It can only push it around. Now, the same trick on the curvature terms. Each comes with an I attached, and because the two i's carry opposite signs, the two terms subtract rather than add. What survives the subtraction folds up into the derivative of a single object, and that object has a name in every other branch of physics. It is a current. The equation that falls out reads that the rate of change of probability at a point plus the rate at which probability flows out of that point equals 0. Probability behaves exactly like water in a pipe or charge in a wire. It is never created and never destroyed. It only moves. Now put the I back where it was, but flip its sign, or make it real, and rerun the same lines. The two potential terms no longer cancel. They add. The two curvature terms no longer subtract. They pile up. What you get is not a conservation law. You get a source term, a place where probability is being manufactured or drained at a rate set by the local potential. A pipe with holes in it. The imaginary unit is the thing that makes those two terms come out with opposite signs. That is its entire job. Multiplication by I is a quarter turn, and a quarter turn one way followed by a quarter turn the other way returns you to where you started. Probability is conserved in this universe because the two halves of a complex number rotate into each other rather than growing into each other. Take the length of an arrow that only ever turns. It never changes. That is unitarity, and physicists write whole books about it, and it is nothing more mysterious than the fact that turning a stick does not lengthen the stick. Someone will say this is a trick of notation. Complex numbers are just pairs of real numbers, so write psi as two real fields and be done with the mysticism. You can. It changes nothing. The two real fields you write down will be coupled to each other in a specific way. The rate of change of the first will be set by the curvature of the second, and the rate of change of the second by the curvature of the first, with a minus sign attached to exactly one of them. That minus sign is I. The rotation is I. You have not removed anything. You have taken the arrow apart into its shadow on the wall and its shadow on the floor, and now you must carry two equations where one would do, and the two are locked together by a 90-degree twist you cannot untie. The complex number is not the mystery. It is the compression of the mystery into one symbol. One more thing the angle refuses to be. Turn every arrow in the whole wave by the same amount, and nothing observable changes anywhere, in any experiment, ever. The overall angle of psi is a quantity nature does not carry. But turn one region of arrows and leave another region alone, and the difference between the two angles is measurable, and it is measurable in the only way anything is measurable in this theory. It shows up as a change in where particles land. Absolute phase, invisible. Relative phase, the whole ballgame. There is a payoff hiding in the current we derived, and it caught me off guard the first time somebody pointed at it. Write out what the probability current contains, and you find it depends on how fast the phase of psi changes from point to point. not on the length of the arrows, on the rate at which their angles wind. If psi is a real function, with no imaginary part anywhere, then there is no winding, and the current is exactly zero. A real wave carries no probability anywhere. It sits. It may oscillate up and down, it may have humps and nodes, and nothing flows. So a particle that is going somewhere requires a complex psi. The unmeasurable angle, the one that vanished when we squared the arrow to get probability, is the only thing in the entire theory that makes motion possible. What you cannot observe is what carries the particle across the room. The observable part tells you where it is. The invisible part tells you where it is headed, which turns the accounting from the last stretch of our work upside down. The phase looked like the discarded half, the part squared away and thrown out. It is the half that moves. Length without angle is a photograph. Angle is what makes the photograph the frame of a film. And there is a quiet fact sitting at the end of that sentence, waiting for us. If a real wave function carries no current, then a real wave function describes something that is not going anywhere. An electron trapped inside an atom is not going anywhere, in the sense that it stays. So perhaps the waves that describe trapped things are, in some way we have not yet earned, real ones. Perhaps confinement is what turns a corkscrew into a standing shape that does not travel. Nothing in the equation has changed. All we would be doing is closing two walls around it. What happens to a wave that can never leave the room it is in? Before we build a wall, notice something about the equation that has been true since we wrote it and that we have not used. The landscape V sits there as a function of position. In most situations of interest, it does not also change with time. A proton pulls on an electron with the same funnel today as tomorrow. A wall stands where it stands. When V depends on x and not on t, the equation offers a gift that mathematicians have exploited for 2 centuries. Guess that psi comes apart into 2 factors, one that knows only about space and one that knows only about time. Call them phi of x and f of t multiplied together. Push that guess into the equation. The time derivative touches only f. The curvature touches only phi. Divide the whole line by phi times f, and something startling has happened. Everything on the left involves t and nothing else. Everything on the right involves x and nothing else. 2 expressions, equal to each other, that share not one variable. Vary t, and the right side cannot respond. Vary x, and the left side cannot respond. The only way 2 such expressions can stay equal is if neither ever changes. Both equal the same constant for all time, everywhere. Call that constant E. The units force the name. 2 equations fall out of one. The time half says the rate of change of f equals minus IE over h bar times f. We have met that shape before, and its solution is an arrow of fixed length turning at rate e over h bar. E to the minus IET over h bar. Nothing but rotation. The space half says that the kinetic energy instruction applied to phi plus v of x times phi equals e times phi. Written compactly, h acting on phi equals e times phi. The eigenvalue equation from before, now standing on its own, with no time in it anywhere. Physicists call it the time-independent Schrödinger equation, which is a poor name, since time has not gone anywhere. It has been factored out. Look at what the pair describes. The shape phi is frozen. The whole wave rotates in place, every arrow at every point turning at the same rate, all together, like the spokes of a wheel. Take the length squared to get probability, and the rotation cancels itself out, since an arrow's length does not care where it is pointing. The probability of finding the electron anywhere does not change. Not now, not in an hour, not in a billion years. These are the stationary states, and the name has misled generations. Nothing is standing still. Everything is turning. What stands still is the only part you can see. The promise made earlier comes due here. If phi can be chosen real, the arrows point along one line. The phase has no winding across space, and the probability current is zero everywhere. An electron in a stationary state is not orbiting anything. Nothing is flowing. The wave is standing, in the exact sense a guitar string stands when it sounds an open note. Which is also the answer to a question that killed the old atom. An electron in orbit around a proton is an accelerating charge, and accelerating charges radiate, and a radiating electron should spiral into the nucleus in about 10 trillionths of a second. Every atom in the universe should have collapsed before it finished forming. The stationary state does not radiate because there is nothing in it that changes. The equation solved that in a line, without a rule against it, without a postulate. So build the wall. Take a particle on a line, free to move between 0 and L, and make V rise to infinity at both ends. A perfectly hard box. Outside, the potential is infinite, so no finite energy can put the particle there, and phi is 0. Inside, V is 0, and the equation says the curvature of phi equals a negative constant times phi. A function whose curvature is proportional to minus itself. Sines and cosines, both of them. The walls do the rest. The wave cannot jump. If phi is 0 just outside the wall, it must be 0 at the wall, since a discontinuity in the wave would give an infinite curvature and therefore an infinite kinetic energy. Cosine has its maximum at the origin, so it dies immediately. Only the sine survives. And at the far wall, sine of k times L has to vanish. Sine vanishes at 0, at pi, at 2 pi, at every whole multiple of pi and nowhere else. K times L equals n times pi, where n is a whole number. Nothing in the equation said anything about whole numbers. The equation is a statement about continuous curvature, written with derivatives, containing no arithmetic of counting anywhere in it. The integers came out of the walls. Fit the wave in the box, and only certain wavelengths close properly, exactly as only certain wavelengths close on a guitar string held at both ends. Pluck the string and you hear one pitch and its overtones, never the frequencies in between, and no one calls that a mystery. The mechanism there is that a wave with any other wavelength arrives back at the bridge out of step with itself and cancels itself into silence. The same cancellation is at work here, in the same mathematics, and what is being cancelled is the probability of the electron existing in that state at all. Translate K into energy through what we already have. Momentum is h bar k, and energy for a free particle is p squared over 2m. Substitute K equals n pi over L, and out comes the answer. Energy equals n squared times h squared over 8ml squared. Quantized energy from geometry in 4 lines of algebra. 2 details finish the picture of these states, and both are checkable in a minute. The demand that the electron be somewhere inside the box fixes the height of the sine wave, and it comes out as the square root of 2 over L, whatever the state. And the number n counts something you can see. The lowest state is a single hump filling the box. The second has one point in the middle where the wave is exactly 0, a place the electron is never found, sitting between 2 humps where it often is. The third has 2 such dead points. The fourth has 3. More humps means sharper curvature, and sharper curvature means more kinetic energy, which is the same statement the equation made about a corkscrew winding tightly. The energy ladder and the node count are one fact wearing 2 hats. Run the numbers on a real box. Confine an electron to 1/10 of a nanometer, roughly the width of an atom. Its lowest allowed energy is about 38 electron volts, and the next level up sits 3 times higher. Those are the energies of ultraviolet light, and they are the reason atoms interact with light the way they do, rather than glowing dully at every color. Now put a grain of dust in a box a centimeter wide. Its lowest allowed energy comes out around 10 to the minus 55 joules. To lift that grain of dust from its first level to its second, you would have to supply an energy so small that it is 100,000 billion times less than the energy a single molecule of air carries at room temperature. The levels are still there. They are separated by nothing. The world looks continuous because we are enormous, and for no other reason. Then there is the number that is not allowed. Set n to 0. The wavelength becomes infinite. The sign flattens to a straight line at 0, and phi vanishes everywhere in the box. A wave that is 0 everywhere means a probability of 0 everywhere, and the particle is not in the box. So n starts at 1, and the lowest energy is not 0. A particle in a box can never be at rest. Being confined costs energy, permanently, and the tighter the box, the higher the bill, since L sits in the denominator squared. Halve the box, and the minimum energy quadruples. Nothing is holding the particle still, because nothing can. To sit still, it would need 0 curvature, and 0 curvature does not fit between 2 walls. I do not know a cleaner example of the difference between this theory and the one it replaced. Newton would let a marble rest at the bottom of a bowl, motionless, for eternity, and nothing in his mechanics objects. Here, the demand that the wave be continuous, that it fit, that it vanish where it cannot go, is enough to give a trapped thing a permanent, irreducible jitter that no amount of cooling can remove. Liquid helium never freezes at ordinary pressure, no matter how cold you make it. The jitter is why. The box was made of 2 flat walls and a lot of convenience, and no such box exists. The real traps in nature curve. If a hard wall can force whole numbers out of a smooth equation, what does the funnel of a proton force out of it? Swap the 2 flat walls for the only trap nature builds. A proton sits at the origin, pulling on an electron with a force that weakens as the square of the distance, and the landscape that force comes from is a funnel. V falls off as 1 over r, deep and steep near the center, shallow and flat far away, never quite reaching 0 anywhere in the universe. No walls, no edges, a hole with no bottom, drawn by Charles Augustin de Coulomb in the 1780s, that the electron is supposed to fall into. 3 dimensions now, so the curvature term counts bending in all 3 directions and adds them together. The equation looks heavier, and it has not changed at all. Total energy equals curvature plus landscape, acting on the wave. The funnel is round, so use round coordinates. Distance from the proton, and 2 angles that say which way you are looking. Try the same split that worked before. Let the wave be a function of the distance, multiplied by a function of the 2 angles. The variables separate again, and the equation falls into 2 pieces that do not speak to each other. Take the angular piece first. Walk once around the proton, all the way around, and come back to where you started. You are at the same point in space. The wave has to have the same value there, since a point has 1 value. The phase of the wave, wound around that loop, must therefore come back to itself after a full circle. It can wind once, or twice, or not at all, but it cannot wind 1.5 times. A whole number of windings, or the wave contradicts itself. The integer that counts those windings is called m, and it fell out of nothing but the fact that a circle closes. Do the same on the sphere, and a second integer appears, called L, counting how many surfaces of zeros the wave carries across the sphere's face, the way a drumhead can vibrate with one still line across it, or two, or none. The allowed angular shapes have been known to mathematicians since Pierre-Simon Laplace, who needed them for the gravity of a lumpy Earth, and they are the same shapes. The universe does not make a new mathematics for each of its problems. Now the radial piece. Far from the proton, the funnel is nearly flat, so the equation there says the curvature of the wave equals a positive constant times the wave if the total energy is negative. A function whose curvature is proportional to plus itself is not a sine. It is an exponential, and it either explodes or dies. An exploding wave has infinite probability far from the atom, which is nonsense. So the dying solution is the only one admissible. The wave must fall away to nothing at large distance, and it must not blow up at the origin either. Two demands, at two ends of a line, on a single continuous function. That is the same trap the box laid, dressed differently. Pick an energy at random and integrate the equation outward from the center, and the tail almost always swings off to infinity. Only for particular values of E does the tail lie down and go quietly to zero. Those values are the allowed energies. And what falls out has been sitting in a spectrometer since 1885. The energy of the level labeled by N equals minus 13.6 electron volts divided by N squared. Minus 13.6 for the lowest. Minus 3.4 for the next. Minus 1.5. Minus 0.85. Crowding up toward zero as N grows, never reaching it. 13.6 electron volts is the energy an electron picks up falling through 13.6 volts of battery, and it is the price of tearing a hydrogen atom apart. Johann Jakob Balmer was a Swiss schoolteacher who, in 1885, at the age of 60, found a formula that reproduced the 4 visible lines of hydrogen to 5 figures. He had no idea why it worked. He was fitting numbers, and he said so. Johannes Rydberg generalized it 3 years later, and for 40 years that formula sat in every physics textbook as a fact without a father. Schrödinger's equation, solved for a funnel, produces Balmer's formula on the way past. Not fitted, derived. Take the difference between two of those levels, divide by Planck's constant, and you have the frequency of the light the atom emits when it drops from one to the other. Drop from the third level to the second, and the energy difference is 1.89 electron volts, which is red light at 656 nanometers, the deep red line in every hydrogen lamp and in the arms of every spiral galaxy anyone has photographed. The 3 integers arrive with rules attached, and the rules are not decrees. The number L cannot equal or exceed N, and M cannot exceed L in size. Both restrictions come from the same accounting. A wave has only so much room to have zeros in. Spend them on angular structure, and there are fewer left for radial structure, and N counts the total. Which is why the first level has exactly 1 shape, the second has 4, the third has 9. N squared shapes at level N, and the periodic table's row lengths are that arithmetic, doubled by a property of the electron that Schrödinger's equation does not contain and knows nothing about. Look at the lowest state. It has no angular structure at all, so the wave depends only on distance, and it is a simple decaying exponential, largest at the proton and fading outward. Real everywhere, which we know already means no probability current, nothing flowing, nothing orbiting. The electron in a hydrogen atom is not going around anything. It is a standing cloud, and the cloud does not move, and the atom does not radiate, and the collapse that classical physics predicted in 10 trillionths of a second simply never begins. A subtlety hides in that cloud. The wave is densest exactly at the proton. Yet if you ask where you are most likely to find the electron, the answer is not at the proton. It is at a distance of about 5/100ths of a nanometer. Both statements are true, and they are not in conflict. Probability per unit volume peaks at the center, but there is almost no volume at the center. A thin shell at distance r has an area that grows as r squared, so the chance of finding the electron somewhere in that shell is the density times a growing amount of room. Multiply a falling exponential by a rising square, and the product peaks in the middle. That peak is the size of the atom, and its value comes out of the equation as a combination of Planck's constant, the electron's mass, and its charge. Nothing was put in by hand. Why does matter have a size? Why does the electron not fall in? Squeeze the wave into a smaller region, and its curvature must sharpen, and sharp curvature is kinetic energy, rising as 1 over the square of the size. The Coulomb funnel offers energy back as it pulls the electron inward, but only as 1 over the size, not the square of it. Shrink far enough, and the kinetic cost outruns the electrical reward, always, at a size fixed by the constants of nature. The atom's radius is the truce line between confinement and attraction. The reason the floor holds you, the reason your hand does not pass through the table, is a curvature term in a 100-year-old equation refusing to be squeezed. I keep a certain respect for how much this leaves out. The spectrum that comes out of this equation is right at the level of coarse structure and wrong in its fine details, because the electron carries a spin nobody had discovered when Schrödinger did the calculation, and because a fast electron near a proton is a relativistic object. Those corrections were built by others, and they are small, parts in 10,000, and they matter. This equation is not the final word about a hydrogen atom. It is the first word that was true. Every stationary state we have found sits still and radiates nothing. Balmer's red line exists. Hydrogen lamps glow. Galaxies are red at that exact wavelength because atoms out there are emitting. If nothing in a stationary state ever changes, what is an atom doing at the moment it makes light? Look at the equation for a property so plain it slides past you. Psi appears once in every term. Once on the left, once inside the curvature, once beside the landscape. Never squared. Never multiplied by itself. Never inside a sine or a logarithm. Every term is psi, or a derivative of psi, times something that has nothing to do with psi. Suppose psi 1 solves it. Suppose psi 2 solves it. Add them with any weights you like, a times the first plus b times the second, and feed the sum into the equation. Every operation in the equation is a derivative or a multiplication by a fixed function, and both of those distribute across a sum. The derivative of a sum is the sum of the derivatives. So the left side becomes a times the left side of the first equation plus b times the left side of the second, and the right side does exactly the same, and both were already equal. The sum solves the equation. Automatically. Always. No physics went into that argument. Only arithmetic. Physicists call this superposition, and the word has been carried off by people who use it to mean the universe is in 2 places at once, and hopes you will not ask questions. The mathematics is quieter. Add two solutions, get a solution. The same statement is true of the equation for sound in air, and nobody has ever written a book about the mysticism of a chord. Two flutes play, and the air carries the sum, and each note passes through the other unharmed. Light behaves the same way, which is why two beams cross in a dark room, and neither is scattered by the other. Water waves at large amplitude do not, and Newton's law of gravity does not, and that is why three bodies orbiting each other cannot be solved and two can. Linearity is a rare gift. Schrödinger's equation has it, exactly, with no approximation. Now spend it. Go back to the two slits. Open the left slit alone, and the wave that reaches the screen is some psi from the left. Open the right slit alone, and you get psi from the right. Open both, and the wave arriving at the screen is the sum, because the sum is a solution, and the equation permits no other. Square the sum to get the probability. The square of a sum is not the sum of the squares. It is the sum of the squares plus a cross term, and the cross term is where physics lives. That cross term contains the product of one wave with the reversed arrow of the other, and what survives is the length of one arrow times the length of the other times the cosine of the angle between them. The angle between them. The phase, the unmeasurable quantity that dropped out of every single slit measurement, reappears as a difference. One wave has traveled slightly further than the other to reach a given point on the screen. That extra distance winds its arrow slightly further around. At the center of the screen, the two paths are equal, and the arrows agree, so the cosine is 1, and the probability is doubled and more. Step sideways until one path is half a wavelength longer, and the arrows point in opposite directions, and the cosine is -1, and the two probabilities subtract to nothing. Electrons never land there. Not because they are forbidden, because the wave cancels itself, and the wave is what decides. Step further. One full wavelength of extra path, and the arrows realign, and a bright band appears. That is the stripe spacing we measured with a ruler in the beginning, and it depends on the wavelength, and the wavelength is h over the momentum, and the entire loop closes. Notice what had to be true for this to work. Probabilities do not interfere. Add two probabilities, and you get a bigger probability, always, with no cancellation possible, since probabilities cannot be negative. The stripes require negative contributions. So, the thing that adds cannot be the probability. It has to be something that can point in opposite directions and whose square is the probability. That is why psi carries units of the square root of a probability density, which sounded like a curiosity when we found it, and is now the reason the pattern exists. Nature does not add chances. It adds arrows and squares the total. Turn on the witch slit detector and follow the arithmetic. The detector's own state now differs depending on the root, so the full wave is no longer two arrows to be added at the screen. It is two arrows attached to two different states of a large object. The cross term contains the overlap between those two detector states, and if the detector reliably distinguishes the routes, that overlap is 0. The cross term vanishes, and the probability becomes the plain sum, and the stripes are gone. Nothing was disturbed. Nothing was pushed. A term went to 0 because two states of a machine stopped resembling each other. Now aim the same trick at the atom. Every stationary state we found is frozen. Its probability cloud does not move. An atom sitting in one of those states is not doing anything. Yet hydrogen lamps glow red. Add two stationary states. Take the state with energy E2 and the state with energy E3, and let the electron's wave be a mixture of both. The equation permits it, since the sum of solutions is a solution. Each piece rotates in time at its own rate, one at E2 over h bar, the other at E3 over h bar. Now square the total. The two squared terms are frozen clouds. The cross term, once again, carries the angle between the arrows, and that angle is now growing with time, at a rate equal to the difference of the two energies divided by h bar. The probability cloud sloshes. It swells on one side of the proton, drains, swells on the other, back and forth, at a frequency equal to the energy difference divided by Planck's constant. A cloud of charge, sloshing back and forth at a definite frequency, is an oscillating electric dipole, and an oscillating dipole radiates light at the frequency of its oscillation. That has been known since Heinrich Hertz. Put in the third and second levels of hydrogen. The energy difference is 1.89 electron volts. The sloshing frequency comes out at 457 trillion cycles per second, and that light is red at 656 nanometers. The color of a hydrogen lamp is the beat frequency between two of its own energy levels. Niels Bohr had to assume that relation in 1913, as a rule handed down with no reason underneath it. Superposition produces it as arithmetic. That argument buys less than it seems to, and the shortfall is instructive. It explains why the light comes out at that frequency and no other. It does not explain why the atom starts sloshing in the first place, or why a lone excited atom eventually decays when nothing appears to disturb it. Schrödinger's equation, left to itself, keeps an excited stationary state excited forever. The decay requires the electromagnetic field to be quantized too, with its own restless vacuum, and that is a later theory built on top of this one. What we have here is the frequency, exact and derived. The trigger came in 1927 from Paul Dirac, and it needed a field with its own psi. And an atom in that mixture has no definite energy at all. Ask it the energy question, apply the energy instruction to the sum, and no single number comes back out front because the two pieces answer differently. Measure the energy and you get E2, or you get E3, with odds set by the squared weights, and never anything in between. Before the measurement, there is a wave doing something perfectly definite in time. After it, there is one number. The lamp glows because atoms are caught between two answers. We have used addition to build interference and to make an atom radiate. There is one thing left to build with it, and it lives on the far side of a wall. Take a wave with less energy than a barrier standing in its path. Inside that barrier, the equation demands that the curvature of psi have the same sign as psi itself. A wave that curves away from zero instead of back toward it does not oscillate. What does it do? Roll a marble at a hill it does not have the energy to climb, and it comes back. Every time, without exception, in a universe governed by Newton, the marble stops where its kinetic energy runs out and rolls back down, and the far side of the hill might as well not exist. Now put an electron in front of a barrier it cannot afford, and ask the equation what psi does there. Inside the barrier, the potential V exceeds the total energy E. Rearrange the equation for that region, and it says the curvature of phi equals a positive constant times phi. Positive, not negative. That single sign change ends the sines and cosines. A function whose curvature bends it away from zero, always, in whatever direction it already points, cannot come back and cross the axis. It cannot oscillate. It can only grow, or it can only decay. Growing is not allowed, since a wave that swells inside a wall would leave the far side larger than it entered, and there is nothing there to feed it. So inside the barrier, the wave is a decaying exponential, e to the minus kappa x, and kappa is the square root of twice the mass times the energy deficit, divided by h bar. The deeper the deficit, the faster the decay. The heavier the particle, the faster the decay. The wave inside the barrier is small. It is not zero. Classical physics has no sentence for that. And it cannot be zero because of a demand we already met at a hard wall. Psi has to be continuous, and so does its slope, or the curvature blows up and with it the kinetic energy. The wave arrives at the barrier with a certain height and a certain slope, and whatever lives inside the barrier must match both at the boundary. A wave with a non-zero height at the entrance cannot become zero the instant it steps inside. It has to descend smoothly, and an exponential descends without ever reaching bottom. Reach the far wall of the barrier, while the exponential still has some height left, and the wave that emerges on the other side starts oscillating again, smaller but alive. A particle that could not be there is on the far side, traveling away with exactly the energy it had before. Nothing was borrowed. The popular telling of this has the particle taking out a loan of energy against the uncertainty principle, sneaking through and paying it back before anybody notices. That story is a fiction, and it is not in the mathematics. The energy of the particle never changes. The equation contains no lending. What it contains is a wave that fails to stop where a wall stands, because stopping instantly would require a kink, and a kink would require infinite curvature, and infinite curvature would require infinite energy. The wave leaks because it is a wave and continuity is not optional. What comes out the far side is set by how many decay lengths the barrier is thick. The probability of transmission falls as e to the minus 2 kappa L, with L the width. Exponential in the width. Exponential in the square root of the mass. Exponential in the square root of the energy shortfall. Three things, all buried in an exponent, which is where nature hides its most violent sensitivities. The mass term is why you have never walked through a door. A person is about 10 to the 28 times heavier than an electron, and the mass enters under a square root inside the exponent. The transmission probability for a human body meeting a wall is not small in the way a lottery is small. It is a decimal point followed by more zeros than there are atoms in the observable universe, then a 1. Tunneling is not rare for you. It is arithmetic that has no meaning at your size. Put numbers on it, and the exponent turns from a symbol into a machine. An electron facing a barrier 1 electron volt too tall, for it has a decay length of about 2/10 of a nanometer, roughly the width of a single atom. Across a barrier 1 nanometer thick, 5 atoms wide, its chance of getting through is around 1 in 30,000. Now push the barrier wider by the width of 1 atom. The chance drops by a factor near 100. Pull back by 1 atom and it rises by that same factor. A machine built on that sensitivity can see individual atoms, and one was, in 1981. Gerd Binnig and Heinrich Rohrer hung a sharpened metal tip a nanometer above a surface, applied a small voltage, and measured the trickle of electrons tunneling across the gap. Move the tip sideways. When it passes over an atom, the gap narrows by a fraction of an atom's width, and the current jumps by an order of magnitude. The scanning tunneling microscope does not see atoms with light. Nothing can, since atoms are smaller than the wavelength of visible light. It feels them through the steepness of an exponential in a wave equation, and the pictures on the wall of every surface science laboratory in the world are pictures of tunneling probability. The same exponent runs the clocks of the heavy elements. An alpha particle inside a uranium nucleus is trapped by the strong nuclear force, and outside that trap the electric repulsion of the remaining protons pushes it away. Between them is a wall. The alpha particle does not have the energy to climb it. Classically, it never leaves, and uranium is stable forever. George Gamow, in 1928, applied this leaking exponential to that wall, working out how the alpha's small transmission probability, multiplied by the enormous number of times per second it strikes the barrier from inside, gives a decay rate. Look at what the exponential does to those rates. Polonium-212 emits an alpha with about 9 million electron volts and lives, on average, 0.3 of a millionth of a second. Thorium-232 emits one with about 4 million electron volts and has a half-life of 14 billion years, longer than the universe has existed. The alpha energies differ by a factor of 2. The lifetimes differ by a factor of 10 to the 24. 10 to the 24 is roughly the number of grains of sand on Earth, and the difference between an eye blink and the age of everything is that ratio, produced by a factor of 2, inside an exponent. Every rock's radioactive clock, every age we assign to the Earth, is a reading of how thick a nuclear wall is, in decay length. Then there is the light coming through your window during the day. The sun's core is 15 million degrees, and a proton in that furnace carries a kinetic energy of a little over 1,000 electron volts. To touch another proton, it has to overcome an electrical repulsion of several 100,000 electron volts. The shortfall is not marginal. It is a factor of a few hundred. By classical physics, no two protons in the sun ever meet. The sun does not shine. It has no mechanism to shine. It sits there, hot and dark and inert. Arthur Stanley Eddington argued in the 1920s that the sun had to be running on nuclear fusion because nothing else could last long enough, and he was told the core was far too cold. His reply amounted to a suggestion that his critics go find a hotter place. He was right, and he did not know why. He could not have known. The reason was written down 4 years later, in the same exponential we just applied to a metal tip and a uranium nucleus. Protons in the sun do not climb the barrier. They pass through it, rarely. And the rarity is precisely why the sun burns slowly enough to have kept this planet warm for 4 billion years rather than exploding in an afternoon. That last consequence took me a long time to absorb. The exponential is what makes fusion hard. If tunneling were easy, stars would consume themselves in minutes. If it were impossible, stars would never ignite. The sun burns at the rate it does because a wave function decays across a Coulomb barrier at a particular rate, set by the mass of a proton and the value of h-bar. Every photon that has ever warmed your skin began as a wave that leaked through a wall it could not cross. The light you saw this afternoon is the far side of that exponential. None of this is exotic physics. It is the same one line, with a different V, a metal tip, a uranium nucleus, and the core of a star, and the only thing that changes between them is the shape of the landscape and the mass in the denominator. The equation predicted the microscope. It predicted the lifetimes of the elements to within factors that experiment has since confirmed. It predicted a sun that shines. How far has anyone pushed it before it finally said something false? A single electron can be held in one place, alone, for months. Trap it with magnetic and electric fields in a chamber colder than deep space, cold enough that the electron settles into the lowest state of its little cage, and watch it. It behaves like a tiny magnet, and you can measure how strong that magnet is. The number is 1.0015965218059. 17 digits. That is the strength of the electron's magnetism, measured in the natural units for the job, and the last 2 of those digits are still being argued about at the level of 13 in the final place. A team at Northwestern published that figure in 2023, and it is the most precisely measured property of any elementary particle anyone has ever weighed, timed, or counted. Theory produces the same number. Not a similar number. The same digits, in the same order, out to the point where our knowledge of one other constant of nature runs out. Measurement and prediction agree to about 1 part in a trillion. A trillion is a word people say without hearing. Take the distance around the Earth at the equator, 40,000 kilometers, and measure it. An error of 1 part in a trillion is an error of 4/100ths of a millimeter. Half the width of a human hair around the whole planet. That is the gap between what a piece of mathematics says and what an instrument reads. 2 honest qualifications. First, that particular number is not a prediction of the equation we built. It comes from the theory that grew out of it, in which the electron and the electromagnetic field are both described by wave functions of their own and both obey the same evolution rule. The equation on our page is the ground floor of that building. The 17 digits come from an upper story. Second, the agreement is limited not by the theory and not by the trap. It is limited by our uncertainty in the fine structure constant, a number nobody can calculate and everybody has to measure. The theory is waiting for the experimentalists to catch up. Below that summit, the equation itself has been checked in more ordinary ways, over and over, for 100 years. The energy levels of hydrogen come out right. The vibrational frequencies of molecules come out right. The heat capacity of a solid, which classical physics predicted would be constant and which stubbornly falls to 0 as things get cold, comes out right, because the vibrations of atoms in a lattice are quantized and freeze out one by one. The electrical conductivity of copper, the transparency of glass, the color of gold, the reason a diamond is hard and graphite smears on paper. Every one of those is the same equation, with a different landscape. Count what sits in a room with you. Every transistor in the device near your bed is a solution to this equation in a periodic potential, arranged so that a small voltage moves a wave function into a region where it may propagate. Flash memory stores your photographs by tunneling electrons through an insulating barrier, on purpose, using the exponential from a few minutes ago. Lasers work because an atom in an excited state will emit into a mode that already contains light, and that fact is a statement about superposition. The magnetic resonance machine that photographs a torn knee is reading the energy splitting of proton spins in a magnetic field in energy units so small that the difference is 1 part in 100,000 of the thermal jostling around them. Somewhere between 1/4 and 1/3 of the industrial economy of the developed world rests on devices that cannot be designed without this line of mathematics. The people who design them do not treat it as philosophy. They treat it as a specification. A smaller test moves me more than the big ones. A hydrogen atom in its ground state has 2 ways for the electron's spin to sit relative to the protons, differing in energy by an amount so tiny it corresponds to a radio wave 21 centimeters long. That splitting has been measured to 12 digits in a laboratory. The same 21-centimeter line arrives at radio telescopes from hydrogen clouds 10 billion light-years away, redshifted, and after correcting for the expansion of space, it comes back to the same frequency. The equation held there. The equation held then. Nothing about the constants of nature has drifted in the time it took that photon to cross the observable universe. And in 100 years, no experiment has caught it out. Not one confirmed deviation in any regime where it is supposed to apply. Physics has an unhappy history of theories that reigned and then broke, and every physicist you meet is hunting for the crack in this one. And there are large research programs whose entire purpose is to find nonlinearity in the equation, or a hidden collapse mechanism, or a limit beyond which superposition fails. Those experiments keep coming back with the same answer. The equation holds. Set that record against the competition. Newton's law of gravity, the most successful theory of the 1700s, matches observation to 5 or 6 digits before the orbit of Mercury starts drifting away from it. General relativity, magnificent and hard won, has been confirmed to about 5 digits in the timing of binary pulsars, and physicists rightly call that a triumph. Quantum theory is running 12. The distance between 5 digits and 12 digits is not a matter of better equipment. It is a difference of a factor of 10 million in how tightly a piece of mathematics is bound to the world. Now the objection that should be raised, and rarely is. Accuracy is not truth. Claudius Ptolemy's model of the heavens, with its circles riding on circles, predicted the positions of the planets well enough to navigate by for 14 centuries. It was accurate, and it was false. Every wrong theory that lasted was accurate first. So why should a string of matching digits persuade anyone of anything? Because of how the digits were obtained. Ptolemy's system improved by adding circles. Whenever a planet misbehaved, you gave it another epicycle, tuned to fit that planet, doing no work anywhere else. The model absorbed data by growing new parameters, one per observation, and a model that can absorb anything predicts nothing. Count the free parameters in Schrödinger's equation, Planck's constant, and the mass of whatever particle you are describing. That is all. There is no knob. There is nothing to tune. Feed in the charge of the proton and the mass of the electron, both measured elsewhere for other reasons, and the entire spectrum of hydrogen falls out with no adjustment whatsoever. When the theory was extended, the same discipline held. The relativistic version had no free parameters either, and it predicted, before anyone had seen one, that a particle identical to the electron but oppositely charged must exist. Carl Anderson found it in a cloud chamber 4 years later. Tunneling was calculated before the tunneling microscope. The quantized energy of a trapped particle was derived before anyone could trap one. A theory that predicts things nobody expected, using constants measured for unrelated purposes, is doing something an epicycle cannot do. I find the tunneling case the most persuasive, and not because of the microscope. George Gamow used the equation to compute how long a uranium nucleus should live from nothing but the shape of a wall and the mass of an alpha particle. The answer was billions of years. Nobody had told the equation about billions of years. It read that number off an exponential built out of h-bar. There is one more claim people make about this equation. Nobody has shown that it must be true. There is no proof from deeper principles, no theorem that says a universe with waves and probabilities has to obey exactly this line and no other. Attempts exist, and the best of them derive the structure from assumptions that are, themselves, no more self-evident than the equation. We have a statement that works to 12 digits and no explanation for why the universe consented to it. Which is a strange place to be standing at 1 in the morning. The most tested statement in the history of science, verified against a trap holding 1 electron, against the color of hydrogen, against the age of rocks, against the burning of the sun, and against every transistor ever fabricated. Every digit matches. And when you ask what happens when you look at the electron, when the instrument clicks and one value appears out of a wave that held many, this equation, checked to a part in a trillion, does not contain a single word on the subject. Open any textbook on this subject, and you will find 2 rules for how a quantum state changes, printed a few pages apart and almost never sitting on the same page where anyone could compare them. The first is the equation we built. The wave evolves smoothly. It is deterministic, reversible, linear, and continuous. Nothing jumps. Nothing chooses. Given psi now, psi later is fixed. The second rule says that when a measurement occurs, the wave stops obeying the first rule. It jumps, instantly, to one of the eigenfunctions of whatever you measured. Which one? Nobody can predict. The odds are the squared lengths: discontinuous, random, irreversible, and nonlinear. John von Neumann wrote both of these down in 1932, side by side, and labeled them Process 1 and Process 2. He did not derive the first from the second, or the second from the first, and he said plainly that he could not. 94 years later, nobody has. Every property of the second rule is the exact negation of a property of the first, which is not the kind of thing you find in a healthy physical theory. Thermodynamics and mechanics look different, but you can build the first out of the second by counting. Newton's law of gravity and Einstein's look different, and one reduces to the other in a limit you can compute. Here there is no limit, no counting argument, no derivation in either direction. Two dynamical laws, one universe, and a fence between them that nobody can locate. Let us try to locate it, since the trying is what makes the problem visible. An electron passes a slit and travels toward a screen. Before it arrives, its wave is a superposition of arriving here, and arriving there, and arriving over there. The screen is made of atoms. Atoms obey the equation. That is not an assumption we are permitted to drop, since the equation's entire claim to universality is that it applies to matter, and screens are matter. So write down psi for the whole thing. Electron plus screen. The equation is linear, and linearity has no exception. If the electron's wave is a sum, then each term in that sum drives the screen. The term where the electron arrives on the left produces a screen with a flash on the left. The term where it arrives on the right produces a screen with a flash on the right. Both terms are solutions, so their sum is a solution, and the sum is what the equation delivers. The state of the world after the electron hits is a superposition of a screen that flashed here and a screen that flashed there. Not a screen that flashed in one place. The equation has never in its history produced a single outcome. It produces all of them, added, with coefficients. And there is a bookkeeping crime hidden in the second rule that people rarely name. The first rule destroys no information. Run it backward and psi retraces its own history, arrow by arrow. The second rule takes a wave with many arrows and returns one, and every other arrow is gone, unrecoverably, with no record of its length anywhere in the universe. Every physical process we have ever examined conserves information in principle. A burned book scrambles it beyond reading, and the equations still say the ashes remember. Collapse does not scramble. It dilates. Add the photographic plate, and now the plate is in a superposition. Add the amplifier, the wire, the recording computer. Add the graduate student who reads the number off the screen at 4 in the morning. Every one of them is made of atoms and obeys the equation. Every one of them gets folded into the sum. At no point does any term in that equation disappear. Terms in a linear equation do not vanish because something got large, or warm, or complicated, or conscious. And yet, at 4 in the morning, the graduate student sees one number. Somewhere between the electron and the eye, the theory must switch from the first rule to the second, and the theory does not say where. Von Neumann proved something worse than that. He proved that you can put the switch anywhere along that chain, at the screen, or at the amplifier, or at the retina, and every experimental prediction comes out the same. The location of the boundary is undetermined by any measurement. A physical theory contains a boundary whose position has no physical consequence and which therefore cannot be found. John Stuart Bell spent years pointing at that fence and asking what it was made of, and he did not get an answer. Probability, in ordinary life, is ignorance. A coin under your hand is heads or tails, and your 50-50 describes you, not the coin. When you lift your hand, nothing collapses. You learn. Perhaps the electron always had a definite arrival point, and psi describes what we do not know, and the jump is nothing but an update. This explanation is not merely unfashionable. It has been tested, and it fails, and the test is the most important experiment of the last 60 years. Follow the chain. If the electron had a definite slit all along, then the pattern with both slits open would be the pattern from the left slit plus the pattern from the right slit, because ignorance adds probabilities, and probabilities do not cancel. Stripes require the arrows to subtract. So the electron did not have a definite slit. Its wave was not a description of our ignorance about a fact. There was no fact. Now make it precise. John Stuart Bell showed in 1964 that if particles carry definite values for their properties before measurement, and if what you do to one particle cannot instantly affect a distant one, then the correlations between measurements on two separated particles obey an arithmetic limit, a ceiling on how correlated they can be. Quantum mechanics predicts a violation of that ceiling. Experiments have violated it hundreds of times since the 1970s, and by 1982, the results were strong enough to convince most physicists, and by 2015, 4 separate groups had closed every loophole anyone had proposed. John Clauser, Elaine Aspect, and Anton Zeilinger were given the Nobel Prize in 2022 for the work. The universe does not contain a set of definite values waiting to be read out, unless it is willing to let one measurement reach across space and change another. You may have one or the other. You may not have both. So the wave is not ignorance, and the collapse is not learning. Whatever happens when a detector fires, it is not a curtain lifting on a fact that was always there. The other rescue on offer is that large systems behave differently. The screen has 10 to the 23rd atoms. Its state is hopelessly entangled with the air and the light in the room, and interference between a flash here and a flash there becomes unobservable in a fraction of a nanosecond. All of that is true and calculable, and we will spend real time on it. It does not answer this question, and the reason is simple enough to state now. Losing the ability to observe interference between two terms is not the same as one of the terms ceasing to exist. The sum is still a sum. The equation still carries both. What has happened is that the cross term has scattered into the environment, where no one can gather it back. The other outcome has not been removed from the mathematics. It has been hidden. I have gone back and forth on how strongly to put this. This is not a gap in the theory in the way that a missing coefficient is a gap, something a clever graduate student might fill on a Tuesday. The equation is complete. It is checked to 12 digits. It is not missing a term. What is missing is a reason why we ever see one thing happen. A theory that describes everything except the occurrence of events. Erwin Schrödinger noticed this in 1935, and to make it impossible to ignore, he wrote down a system where the amplifier was a hammer, a vial of acid, and a cat. The famous story is not a lesson about mystery. It was an argument that his own equation, taken at its word, predicts something absurd. He meant it as a refutation. Nobody refuted it. The equation still says what it said. 90 years of the best minds in physics have looked at the fence between the two rules, and they have not agreed on what to do about it. They have not even agreed on what kind of problem it is. Where exactly did the men and women who built this thing part company, and why has none of them been able to prove the others wrong? In October of 1927, 29 physicists gathered in Brussels for a week, and 17 of them would eventually hold a Nobel Prize. The argument that started that week is still running. Niels Bohr held one position and Albert Einstein held another, and the shape of their disagreement has been misreported for a century. Einstein was not troubled by randomness in the way a schoolchild is troubled by not knowing. He was troubled because he thought the theory was incomplete, and he kept trying to prove it by constructing experiments that would beat the uncertainty relations. Each morning at breakfast he would present one. Each evening Bohr would come back having dismantled it. The best of them came 3 years later. Einstein imagined a box full of light, hanging from a spring scale, with a shutter timed by a clock inside. Open the shutter for an instant, let one photon escape, and weigh the box before and after. The change in mass gives the photon's energy through E equals mc squared to whatever precision your scale allows, and the clock gives the time of escape to whatever precision you like. Energy and time, both pinned, both sharp, and the uncertainty relation between them broken. Bohr, by the accounts of everyone present, spent a sleepless night. In the morning he answered using general relativity, which was Einstein's own creation. Weighing the box means letting it shift position in a gravitational field. A clock that changes its height in a gravitational field changes its rate. The more precisely you weigh, the more the clock's reading smears. The two uncertainties reappear, exactly at the level the theory demands. Einstein was beaten with his own instrument, and he changed his objection rather than dropping it. The objection he changed to was better. With Boris Podolsky and Nathan Rosen, in 1935, he stopped attacking the uncertainty relations and started attacking the completeness of the wave function. Two particles fly apart from a common origin. Measure the first, and the wave function of the second changes instantly, at any distance. Either that change is a real physical influence traveling faster than light, or the second particle had its properties all along and the wave function never described them fully. Einstein took the second horn. Bohr's reply, read today, is difficult to follow, and physicists still disagree about what he meant. That paper is the one that eventually produced Bell's theorem, and Bell's theorem eventually produced the experiments, and the experiments came down against the horn Einstein chose. Schrödinger read the Einstein-Podolsky-Rosen paper and wrote to Einstein about it within weeks, and out of that correspondence came the cat. A radioactive atom in a superposition of decayed and not decayed, wired to a hammer, a vial of poison, and an animal in a steel chamber. The equation, applied without exceptions, says the whole box ends in a superposition of a live cat and a dead one. Schrödinger was not marveling at the strangeness of the quantum world. He was saying that a theory which predicts this is a theory with a hole in it, and he expected physicists to agree that the conclusion was ridiculous. The cat has been turned, in 90 years of retelling, into an advertisement for the very mystery it was written to protest. I do not think he would have found that funny. So the founders left us a problem and no answer. What came afterward were not experiments. They were positions. The oldest is the one Bohr taught, though there is no single doctrine, and the people usually grouped under its name disagreed with each other constantly. The wave function is not a picture of an electron. It is an instrument for calculating what happens when you set up an apparatus and read a dial. Questions about what the electron is doing between preparation and detection are not answerable because you have no experiment that asks them. The collapse is not a physical process. It is what happens to your description when you learn something. The strength of this position is that it never says anything false. Its cost is that it declines to describe the world when nobody is looking, and it needs a classical apparatus to exist before quantum mechanics can be applied, which is awkward in a universe made entirely of quantum things. The second position is to take the equation completely seriously and delete the second rule. Hugh Everett III wrote this in his doctoral thesis in 1957 at Princeton, under John Archibald Wheeler, and the physics community treated him so coldly that he left research for defense analysis and never came back. His argument is short. The equation is linear. The equation applies to detectors and to people. Therefore, the superposition never goes away, and after the measurement, there is a term describing an observer who saw the left flash and a term describing an observer who saw the right one. Both observers are real. Both remember one outcome. Neither can see the other. Nothing collapsed. Nothing was deleted. The universe contains all the branches, and you are in one of them because you are the one asking. The price is enormous ontology and a hard problem about probability. If every outcome occurs, what does it mean that one had a 90% chance? Everett's answers to that, and the answers of his successors, are debated to this day and are not settled. The third position keeps the particle. Louis de Broglie proposed it in 1927, was argued out of it at that same Brussels meeting, and David Bohm rebuilt it from scratch in 1952. The electron has a position at all times, a real one, a single one. The wave function exists too, as a separate physical thing, and it guides the particle, pushing it along the flow lines of the probability current we derived. Feed in an unknown starting position, distributed according to psi squared, and every prediction of standard quantum mechanics comes out identical. The double slit is resolved simply. The electron goes through one slit. The wave goes through both and steers it. The price is written in the mathematics in plain sight. The guiding wave for two particles depends on both positions at once, so moving one particle instantly alters the guidance of the other at any separation. The theory is explicitly non-local, and its authors said so. Bell, who is often quoted as an opponent of this idea, admired it, and said it made the non-locality visible instead of hidden. The fourth position changes the equation. Add a small random term that makes the wave function spontaneously localize, rarely for one particle, constantly for many. Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber wrote such a model in 1986. A single particle collapses once every 100 million years or so. A speck of dust, containing 10 to the 18 particles, collapses in a fraction of a microsecond. Collapse becomes a physical process with a rate, and the cat is never in two states because the cat is too big. This position is different in kind from the other three. It does not merely reinterpret. It predicts different numbers in delicate experiments, and those experiments are being done. The parameter space has been narrowed considerably in the last 20 years. From underground detectors watching for the tiny heating such a mechanism would cause, and the models are constrained, but not dead. That is what a testable proposal looks like, and it is the reason many physicists respect this direction even when they doubt it. Newer positions exist and they are not fringe. One family holds that the wave function is a catalog of one agent's expectations, so that two observers can hold different wave functions for the same system without either being wrong, and collapse is nothing but a person updating their bets. Another holds that states are always relative, that a fact exists for one system with respect to another and not absolutely. Both dissolve the measurement problem by denying that psi was ever a description of the world in the first place. Whether that is a solution or a refusal to look is exactly what their critics and their defenders disagree about. Set those 5 side by side. Except for the collapse models, none of them predicts anything different from any other. The same digits come out. The same experiments confirm all of them equally. There is no measurement you can perform tomorrow that distinguishes a world of branches from a world of guiding waves, from a world where the question is forbidden. They agree on every number and disagree about what the universe is. Physics has never been in this position before, with a theory this precise and this silent. And every one of them has to explain the same stubborn thing. Why does an atom interfere with itself, and a chair never does? Nothing in the equation forbids a chair from interfering with itself. No term switches off above a certain mass. No clause excludes objects made of wood. The linearity that put a screen into a superposition applies to a chair, a planet, and a person without qualification. So the absence of interference in the world you are lying in has to be explained, not assumed. Start where the fringes come from. 2 arrows, one from each path, added at a point, and the cross term between them contains the cosine of the angle between the arrows. That cross term is the entire pattern. Remove it, and the stripes go, and nothing else changes. Now let the object touch the world. Not be measured, not be watched, simply touched, in the way anything in a room is touched. An air molecule strikes the object while it is spread across both paths. The molecule bounces off in a slightly different direction depending on which path the object was on. The molecule now carries a record. It flies off across the room, hits a wall, warms it by an unmeasurable amount. The record is not destroyed. It is dispersed. Look at what happened to the cross term. The 2 arrows are no longer attached to identical surroundings. One is attached to a molecule flying left, the other to a molecule flying right. The cross term now contains the overlap between those 2 molecular states, and if the molecule reliably distinguishes the paths, that overlap is close to 0. The interference does not weaken because energy was lost. The object never slowed. Nothing was disturbed in any classical sense. The cross term went to 0 because information about the path escaped into something nobody is reading. This has a name, decoherence, and it has a rate, and the rate is what settles the argument. Eric Juice and Heinz-Dieter Zeh calculated it carefully in 1985 for real objects in real environments. A speck of dust, 10 micrometers across, spread over a distance equal to its own width, sitting in ordinary air. Air molecules strike it at a rate of about 10 to the 20 per second. Each collision carries away a little path information. The interference between the 2 locations of that speck dies in something like 10 to the minus 36 seconds, which is a number that no longer means anything to a human being, so hold it this way. A trillionth of a second is to 1 second as 1 second is to 30,000 years. Now take a trillionth of that, and a trillionth of that again. Take the air away and pump the chamber to a perfect vacuum. Sunlight alone, scattering off the speck, kills the interference in about a billionth of a second. Shield it from the sun, close the room, turn off every lamp. The thermal glow of the walls does the job. Cool the walls to a few degrees above absolute 0, and the photons of the cosmic microwave background, arriving from every direction in the universe with nothing capable of stopping them, still decohere that speck in around a second. There is no place in the observable universe where a dust grain can hold a superposition for a minute. Which explains why the world looks classical. It is not that big things obey different physics. It is that big things are impossible to isolate. Interference is not destroyed by size. It is destroyed by contact, and contact scales ferociously with size. A single atom in a good vacuum chamber, cooled, shielded, touches almost nothing, and it interferes. A cat has a surface area of 1/3 of a square meter, radiates infrared photons by the trillion every second, and every one of those photons carries away information about where the cat is. The cat is being measured constantly by the universe, and the record is written into an environment nobody can gather back. So the boundary between quantum and classical is not a boundary. It is a rate. And a rate is a number you can compete with. People have been competing with it for 30 years, and the scoreboard is public. Electrons, then neutrons, then whole atoms, then molecules. In 2019, a group in Vienna sent molecules built from up to 2,000 atoms, with masses beyond 25,000 atomic mass units, through a 2-meter interferometer, and recorded clean fringes. One of them, a tailored porphyrin, contains more than 40,000 protons, neutrons, and electrons in a single object, and its de Broglie wavelength during the flight was 1,000 times smaller than the diameter of a hydrogen atom. That object was in 2 places at once, and the distance between the 2 places was larger than the object. It is heavier than the protein insulin. Nobody has yet found the mass at which the equation stops. Distance has been pushed too. In 2015, a group at Stanford split clouds of rubidium atoms, sent the 2 halves apart, and brought them back to interfere after the separation had reached 1/2 meter. Half a meter. Wider than the span of your 2 hands. A single atom, in 2 places, a hand's width apart, for 2/3 of a second, and the fringes came back exactly where the equation said they would. The people running those experiments are not doing it for the record. Every fringe pattern at a higher mass places a bound on the collapse models, the ones that add a spontaneous localization term to the equation. If wave functions really do collapse on their own at a rate that grows with the number of particles, then a molecule of 25,000 mass units should have shown a measurable loss of contrast. It showed none. The allowed parameter space for those models shrinks with each experiment, and it has not yet closed. This is the one place where the arguments from earlier tonight are being decided by measurement rather than by preference, slowly, 1 order of magnitude at a time. Decoherence explains why you never see interference between a cat that is alive and a cat that is dead. It explains why the world separates cleanly into the outcomes we recognize, position and not momentum, the states that survive contact with air and light. It gives the rate, it gives the preferred set of states, and every number it produces has been confirmed in the laboratory. It does not remove a single term from the equation. After the air molecule flies off, the state of the world is a sum of 2 terms, one with a live cat and a molecule flying left, one with a dead cat and a molecule flying right. Both terms are still there. Their cross-term has become unobservable to anyone who cannot chase down every scattered photon in the universe and bring them back together in phase. Unobservable is a statement about us. It is not a statement about the mathematics. The sum is still a sum. Decoherence turns a superposition you could detect into a superposition you cannot detect, and then hands you the same 2 terms it started with and says nothing about which one you find yourself in. I have read the papers where this is claimed as a solution, and I have read the replies, and the replies win. The measurement problem is exactly as unsolved as it was in 1932, and what has changed is that we now understand, in quantitative detail, why the problem is invisible. We know precisely how the universe hides the question from us. We do not know the answer to the question. So there is no line. There is a molecule of 2,000 atoms interfering in Vienna, and a dust grain that cannot manage it for a second, and between them nothing but arithmetic, a scattering rate, a wavelength, a mass. The same equation runs both, and it runs you. Your body is a warm object in contact with everything, radiating photons in every direction, exchanging molecules with the air in the room, decohering at a rate so fast that no version of you was ever spread across two positions long enough for anyone to notice. That is not an exemption. It is a rate. The equation never stopped applying. It stopped being visible. Everything we have built tonight, the arrows, the curvature, the phase that carries motion, the levels that fit in a trap, is running inside you right now at a scale where the wave is the only thing there is. What exactly is it doing in there? Take the simplest molecule that exists. 2 protons, 1 electron, nothing else. Set the 2 protons a fixed distance apart and ask the equation what the electron's wave does. The landscape now has 2 funnels instead of 1. 2 solutions come back, and they differ in one respect. In the first, the wave has the same sign at both protons, and it does not cross zero anywhere between them. It swells in the middle, filling the gap. In the second, the wave is positive at one proton and negative at the other, so somewhere in between, it must pass through zero. A flat plane of nothing, halfway. Everything about chemistry follows from which of those two costs less. Count the curvature. The wave with a node between the protons has to come down to zero and climb back out, and that bending is sharp, and sharp bending is kinetic energy. The wave without a node stretches smoothly from one proton to the other. It is a longer wave in a wider space. Recall the box, where having the width quadrupled the energy. The electron in the 2-proton molecule has been handed a wider box. Its wavelength lengthens, its momentum falls, its kinetic energy drops. That is the chemical bond, and it is not what most people were taught. The standard story says the electron sits between the 2 protons and glues them together by electrical attraction, like mortar between bricks. The mortar story gets the electron's location roughly right and gets the physics backwards. The dominant saving, when the calculation is carried through without shortcuts, is not electrical. It is kinetic. The electron gains room to spread. A wave with more room has less curvature. Less curvature is less energy. 2 hydrogen atoms bind to each other because a single electron, allowed to be in 2 places at once, is cheaper than an electron confined to 1. The bonds holding every molecule in your body together are the energy saved by letting a wave stop being squeezed. The protons do not fall together, and their reason is the same one that gave the atom a size. Push them closer, and the electron's box narrows again, and its kinetic energy climbs back, and the 2 protons repel each other more fiercely as well. Pull them apart, and the electron loses the room it gained. The balance point for 2 hydrogen atoms sits at 0.07 of a nanometer, and holding them there stores 4.5 electron volts of binding. Every molecular bond length ever measured is a truce between a wave that wants room and a pair of charges that will not share a point. The other solution, the one with the node, sits higher in energy than 2 separate atoms. Push electrons into that state, and the molecule flies apart, which is why not everything sticks to everything. Helium has 2 electrons. Bring 2 helium atoms together, and both the smooth state and the noded state must be filled, and the cost of the second cancels the saving of the first. Helium is a gas that will not bond with itself at any temperature you can arrange in a room. A wave and a node, and the periodic table starts sorting itself. Now the thing the equation does not contain. Nothing we have written explains why both helium electrons cannot simply occupy the smooth low state together and save twice the energy and bond after all. Schrödinger's equation has no rule against it. The rule was found by Wolfgang Pauli in 1925, before the equation existed, and it is a separate law. Two electrons cannot occupy the same state. The full wave function of a pair of electrons has to change sign when you swap them, and identical states leave nothing to swap, so the wave function is zero and the arrangement does not exist. That statement comes from relativity and the spin of the electron, and Schrödinger's line knows nothing about either. It has to be added by hand, and everything you are made of depends on it. Put the two rules together and you have the reason your body occupies space. Electrons fill the low states of an atom and then, forbidden from stacking, are forced up into wider, more curved, higher energy states, further out. Press two atoms together and their electrons must find new states, and every available low state is taken, so the electrons are driven upward in energy. Pushing costs. The stiffness of bone, the resistance of a floor, the impossibility of pressing your palm through the mattress under you is not electrical repulsion between charges, or not mainly. It is the price of forcing waves into shapes they refuse to hold, in a world where no two electrons are allowed the same shape. The same accounting, run on a dying star, is what stops a white dwarf from collapsing under its own weight. The floor beneath your bed and the corpse of a star hold themselves up by the same claws. Come closer in. The molecule that carries your genome is held in its double helix by hydrogen bonds, and each of those bonds has a proton sitting in a landscape with two wells, one near each of the bases it joins. A proton is nearly 2,000 times heavier than an electron, and the exponential we met at the barrier punishes mass. Even so, the barrier is thin. Per Olav Lodin proposed in 1963 that a proton could tunnel from one well to the other, leaving the base pair in a rare alternative form that, at the moment of copying, reads as a different letter. A tunneling event is a source of mutation. Whether this contributes measurably to the mutation rate in living cells is argued about to this day. Recent calculations suggest that tautomer forms far more often than anyone expected and disappears again quickly, and the biological consequence remains unsettled. I am not going to tell you that quantum tunneling wrote your genome. I will tell you that nobody has been able to rule it out, and that the barrier is exactly the shape the equation describes. Where the evidence is firm is in enzymes. An enzyme that moves a hydrogen atom from one molecule to another has to lift it over an energy barrier, and for decades the rates came out faster than the barrier allowed. Replace the hydrogen with deuterium, twice the mass, and the reaction slows by far more than the mass difference should cause. That is the signature of the exponential. Mass sits under a square root inside it, and doubling the mass slows the leak by an amount that classical chemistry cannot produce. Proton and hydrogen tunneling in enzyme catalysis is established laboratory chemistry. It is happening in your liver tonight, in the dark, at a rate set by h-bar. And in your eyes? A rod cell in your retina, fully dark adapted, responds to a single photon. Not a few. One. The photon is absorbed by a molecule called retinal, which sits in a bent shape inside a protein pocket. Absorbing the photon puts the molecule's electrons into a superposition of states that no longer holds the bend, and the molecule straightens in about 200 femtoseconds. 200 femtoseconds is to a second, as a second is to about 150,000 years. That straightening is the fastest reaction known in biology, and it is fast because the wave function does not have to find its way through a barrier. It is released onto a slope. Everything you have ever seen began with one molecule changing shape because an electron's wave changed which arrangement it preferred. None of this makes biology mystical. There is a genre of writing that treats these facts as evidence that living things exploit quantum mechanics in some special way that rocks do not, and I have never found the argument convincing. A rock is quantum. A protein is quantum. Nothing had to be exploited. The point is smaller and stranger than the mystical version. When you look for the reason a bond holds, or a bone is stiff, or an enzyme is fast, or an eye is sensitive, the explanation bottoms out in a wave with a certain curvature, obeying one line of mathematics written in a villa in the Alps 100 years ago. There is nothing under it. That is the floor. Your heart is beating because sodium ions cross membranes, and they cross through channels whose selectivity comes from the energy levels of ions in a narrow pore. Your body is warm because the vibrational states of molecules are quantized and store energy in steps. The oxygen in your blood binds to iron because of the shape of a d orbital, which is a solution to the equation, in 3 dimensions, around a nucleus. The equation is not describing your body from a distance. There is nothing else there. And a single line of mathematics, holding up a floor, a star, a molecule, and an eye, ought to make anyone suspicious. How can something this short be enough, and what has it been quietly leaving out all night? Gold is yellow, and silver is not, and the difference is a failure of the equation we built. Hold that for a moment. Every metal you can name reflects nearly all visible light and comes back gray or white. Gold absorbs blue. What returns to your eye is the rest, and the rest is warm. The absorption happens when an electron jumps between 2 particular levels in the atom, and Schrödinger's equation, solved for gold, puts those levels too far apart. It predicts the jump in the ultraviolet. It predicts silver. Gold should be white. The innermost electrons of a gold atom move at more than half the speed of light. They have to, since the nucleus holds 79 protons and the pull is enormous. At that speed, the electron is heavier than it is at rest, by the factor Einstein wrote down in 1905, and a heavier electron sits in a tighter orbit, and the tightening cascades outward through the whole atom, dragging one level down and pushing another up until the gap lands in the blue. Redo the calculation with relativity included, and gold comes out yellow. Our equation used p squared over 2m, which is the kinetic energy of something moving slowly. That is the first thing it leaves out, and the omission is not academic. Mercury is liquid at room temperature for the same reason. Its outermost electrons pulled so tightly by relativistic contraction that they will barely bond to the next atom. The lead-acid battery in a car delivers about 2 volts per cell, and most of that voltage comes from relativistic effects in the electrons of lead. Take relativity out of chemistry and cars would not start. The second omission is stranger, because the equation does not merely approximate it. The equation has no room for it at all. Nothing inside describes an electron spinning. Send silver atoms through a magnetic field that varies across the beam, and the beam splits in 2, never 3, never a smear. Otto Stern and Walther Gerlach did that in 1922, before quantum mechanics existed, and nobody understood what they had seen. The electron carries an angular momentum that has only 2 possible readings along any axis you choose, and it is not going around anything. Wolfgang Pauli patched the equation in 1927 by bolting on a 2-component wave function and an extra term, and it worked, and he knew it was a patch. Paul Dirac was 25 years old and would not accept the patch. He wanted an equation for the electron that satisfied relativity from the start, and relativity refuses to treat time and space asymmetrically. Our equation has 1 time derivative and 2 space derivatives, an imbalance we noticed and set aside hours ago. Dirac demanded one of each. A single time derivative and a single space derivative in a wave equation, with energy still coming out right. That is close to impossible. Squaring one derivative has to reproduce the relativistic energy relation, and no ordinary numbers can be arranged to do it. He solved it by allowing the coefficients to be objects that do not commute, 4 by 4 arrays of numbers, chosen so their squares and cross products cancel exactly the way the algebra requires. The wave function acquired 4 components, forced by the mathematics, not by observation. 2 of those components describe an electron with angular momentum pointing up or down. Spin fell out. Not inserted. Fell out from the demand that space and time be treated alike. And the strength of the electron's magnetism, the number that had to be measured and stuffed into Pauli's patch by hand, came out of Dirac's equation as exactly 2, which is what experiments said, to the precision of the day. The other 2 components were a catastrophe. They described states of negative energy, an infinite ladder of them descending forever, into which every electron in the universe should immediately fall, radiating light as it went. Matter should evaporate in a flash. Dirac spent 2 years on it, proposed that all the negative states are already occupied in full, and that a hole in that filled sea would behave like a particle with the electron's mass and the opposite charge. He first guessed the proton, and was told the masses did not match. In 1931, he wrote that the particle must be a new one, unobserved. Carl Anderson photographed it in a cloud chamber in 1932, a track curving the wrong way in a magnetic field, and antimatter existed. A demand for symmetry between space and time, written on paper, produced a particle nobody had asked for. Even Dirac's equation is not the end. Push 2 electrons together hard enough, and you can make more particles out of the collision energy. Particle number is not conserved, and a wave function of 1 particle, or 2, or a wave function living in 18 dimensions, has no way to describe a world where the count changes. The fix is to stop treating psi as the wave of a particle, and treat it as a field spread through space, with its own equation, whose excitations are particles. 1 quantum of excitation, 1 electron. 2 quanta, 2 electrons. Create and destroy them as the energy allows. That is quantum field theory, and it is where the 12 matching digits of the electron's magnetism come from. And every one of those theories is built on the same line. Look at what changed and what did not. Dirac's equation for the electron, the equation for the photon field, the theory of quarks, the Standard Model itself. Write any of them in the form where you track how the state of the world evolves in time, and you find the identical sentence. I, h bar, times the rate of change of the state equals h acting on the state. The state is no longer a function of one position. H is no longer curvature plus a landscape. The skeleton has not moved. That is why one line is enough. Schrödinger's equation was never a statement about electrons. It is a statement about how any quantum state changes when nobody looks. The physics of a particular problem lives entirely in H, and H is a bucket you fill with the situation you care about. Change H, and you go from a hydrogen atom to a superconductor to a quark inside a proton to the interior of a neutron star. The bucket changes. The pouring does not. Every interpretation from earlier tonight, however violently its defenders argue, keeps that pouring untouched. Branches, guiding waves, agents updating their bets, all of them accept that between measurements, the state turns without changing its length. The fight is about what psi is and what happens when we look. Nobody has proposed abandoning how it moves. Which reframes what we spent the night doing. We did not derive the law of quantum mechanics. We derived the simplest h, the one for a slow particle in a landscape, and discovered that the frame around it is older and larger than the particular case. Every extension since has kept the frame. Nobody has found a reason to break it. Gravity is not a landscape. In general relativity, gravity is the shape of space-time, and the shape responds to matter, and matter is described by psi. So put a mass in a superposition of two positions. What does space-time do? It has to curve toward both places at once, and the equations of general relativity have no term for that. They take a definite distribution of mass and return a definite geometry. Nobody has written the equation that governs a superposed geometry, not for lack of trying, and not for lack of ideas, and there is now serious talk of experiments with milligram masses that might tell us whether gravity is quantum at all. Until one of them runs, this is the oldest open question in physics, and it is not close to settled. I take a certain comfort from an equation that tells you where it stops. Slow particles. Fixed particle count. No spin unless you add it. No gravity. Inside that boundary, it has never been caught wrong. Outside it, its own descendants took over, and they kept its shape. A theory that knows its own domain earns more trust than a theory that claims everything, and I would rather hold this one, with its edges marked, than a grander thing that explains too much. We began with 2 measurements and a corkscrew of arrows. We have arrived at a frame that holds up chemistry, stars, computers, and every extension physics has built in 100 years. Could you rebuild the whole thing now, from the 2 measurements forward, before your breathing slows? Let us lay the whole night out on a table and separate what was measured from what was reasoned. The distinction matters more than the conclusion. A chain is only as strong as the honesty about which links were forged in a laboratory and which were argued into place. 3 things were measured, and nothing else was. The first is that a single electron, alone in a dark chamber, crossing a barrier with 2 openings, lands somewhere the arithmetic of a wave permits, and never lands where that arithmetic forbids. Nobody reasoned that into existence. A photographic plate recorded it, dot by dot, and the stripes appeared while the physicists watched. The second is that the energy of light comes in units set by its frequency, a fact pulled out of the glow of a furnace and then confirmed, unwillingly, by a man who spent a decade trying to disprove it. Energy equals a constant times frequency. The third is that momentum and wavelength trade against each other by the same constant, a proposal made in a doctoral thesis and confirmed 2 years later by an accident with a broken vacuum flask and a piece of nickel. Momentum equals the constant divided by wavelength. That is the entire experimental input. 1 pattern on a screen and 2 exchange rates. Now the reasoning, and I want to number the steps the way you would if you were rebuilding this yourself on a napkin. A free electron drifting through empty space must be described by something that does not single out one location. A cosine fails, since its zeros nailed dead points into a vacuum that has no landmarks. The only function that oscillates without ever having a zero is a complex exponential, an arrow of fixed length turning at a steady rate. That was not a choice. That was the last object standing after the requirements were applied. Differentiate that arrow in time and it hands back a copy of itself with its frequency out front. Multiply by I and by h bar, and the frequency becomes energy. Differentiate along space, and the same thing happens with wave number. And with the right factor out front, the wave number becomes momentum. Energy and momentum stopped being numbers and became instructions. Nothing was assumed. 2 measured exchange rates, applied to a forced function, produce 2 operators. Then we borrowed one sentence from before quantum mechanics. Kinetic energy plus potential energy equals total energy. A statement that survives from Leibniz through a paddle wheel, through Emmy Noether's proof that it holds, because the universe has no preferred moment. That sentence was not derived tonight. It was inherited. And then, exactly once, somebody guessed. Schrödinger let each symbol in that inherited sentence stop being a number and start being an instruction acting on the wave. There is no theorem behind that step. There is no argument that forces it. He wrote it down over a Christmas holiday, and it worked. One guess in the whole architecture. When the free electron is fed back into the result, the classical sentence comes out unchanged on the far side, which is the only kind of receipt physics accepts for a guess. One more thing had to be added, and it was added in a footnote. Nothing in the equation says what psi means. Max Born wrote, in a correction made while the type was already set, that the squared length of the arrow gives the probability of finding the particle. That rule has never been derived from the equation it accompanies. It is a second law standing beside the first. Count the ledger. 3 measurements. 1 inherited conservation law. 1 guess. 1 rule appended in a footnote. Everything else in this entire night has been arithmetic. Everything. The imaginary unit is the thing that keeps probability from leaking out of the world, because a quarter turn one way and a quarter turn the other cancel, and an arrow that only turns never shortens. Remove it, and matter evaporates. Confine a wave, and its wavelengths must fit, and only whole numbers of half wavelengths fit, and energy comes in steps. Nobody put the integers in. The walls did. Replace the walls with the funnel of a proton, and the same fitting produces the exact numbers a Swiss schoolteacher had extracted from 4 red and blue lines in 1885 with no explanation, 40 years before anyone knew where they came from. Add 2 solutions and you get a solution, and the cross term between them is the stripes on the screen from the first minute of tonight, and it is also the color of a hydrogen lamp, and it is also the reason a detector at a slit erases a pattern without touching anything. 1 piece of arithmetic, 3 phenomena. Let a wave meet a wall it cannot climb, and continuity forbids it from stopping abruptly, so it descends through the wall as a fading exponential and comes out the far side smaller and alive. That leak is why uranium decays, why a tip can feel a single atom, why the sun burns slowly enough to have warmed this planet for 4 billion years instead of detonating in an afternoon. I have written that chain out many times, and there are 2 places where I still stop. The first is the letter I. It entered because a wave needed to turn instead of flicker. It stayed because probability must be conserved. Neither reason has anything to do with the other, and yet the same symbol does both jobs. A number invented in the 1500s to handle roots that could not exist is the only thing preventing matter from draining out of the universe. Nobody planned that. Nobody has explained it. The second is the footnote. A theory whose central equation is deterministic, reversible, and continuous, checked against a trapped electron to 12 decimal places, has to be handed a separate sentence, by hand, in order to say why anything ever happens. 94 years of the sharpest people alive have not managed to fold that sentence into the equation. They have divided into camps that agree on every number and disagree about what exists. And the universe, meanwhile, keeps declining to comment. There is a third thing, smaller, that I notice mostly when the house is quiet. The stripes on that screen do not care whether anyone reads the Witchpath record. They care whether the record exists. A pattern of light on a wall, governed by whether a fact is available somewhere in the world, in a molecule flying off into a room nobody will ever enter. Physics was supposed to be about forces and masses. This is a law about knowability, written into where electrons are permitted to land. I have never made peace with that, and I have stopped expecting to. Consider what you have done tonight. You started with a screen full of dots. You now know why the dots make stripes, why the stripes vanish when someone watches, why atoms have a size, why the floor holds you up, why gold is yellow, why the sun is warm. You could sketch the equation from memory. Not because you memorized it, because you watched where each symbol came from, and there was nowhere else for any of them to go. It took the human species about 30 years to walk that road. Planck in 1900, Einstein in 1905, de Broglie in 1923, Schrödinger in 1925, Born in 1926, Dirac in 1928. 6 people, 3 decades, 1 line. They did not know they were building it. Each of them thought they were repairing something else. The equation is running now, in the wall beside you, in the air, in the mattress, in the water in your cells. Not as a description, as the thing itself. There is no version of the world underneath it that behaves the way the world looks. The table is not solid, and the electron is not a dot, and the atom is not a little solar system, and none of that was ever a metaphor we chose to abandon. Each of those was a picture we held until an experiment took it away. The room you are in is dark. Your breathing has slowed while we worked, the way it does. And every one of the 100 billion arrows that make up the body lying on that bed is turning right now at a rate set by its own energy, keeping its length exactly, obeying a line of mathematics that a tired man wrote in a rented villa in the mountains, and that nobody has been able to break since. What, precisely, is that line doing in the dark, in you, tonight? The last light that reached you today came out of the core of the sun. 2 protons met there, in a place too cold to allow it, and one of their waves leaked through a wall it could not climb, and they fused. The energy that came off that meeting has been working its way outward ever since, absorbed and re-emitted by hot matter, wandering, taking tens of thousands of years to cross a distance that light in open space would cross in 2 seconds. Then 8 minutes across the emptiness. Then a window. Then the back of your eye, where 1 molecule bent inside a protein pocket in 200 femtoseconds, and you saw the afternoon. That photon is gone now. The room has gone quiet. The stars that made the atoms of your body are gone too, most of them, spent long before the sun existed. What they left behind was not warmth or light. It was a set of nuclei with particular charges, each one carving a particular funnel, each funnel permitting a particular set of shapes. Every property of every material you have ever touched was decided the moment a nucleus acquired its number of protons and a wave was told which shapes would fit. What has not stopped is everything else. Your body has about 7 billion atoms in it. Every one of them is a solution to the equation we built tonight, standing in the funnel of its own nucleus, holding a shape that does not change while the arrows inside it turn. Nothing is orbiting. Nothing is circling. The clouds are still, and the phase beneath them rotates, each at a rate fixed by its own energy, and has been rotating since those atoms were assembled inside stars that are no longer there. The mattress does not let you through. Not because the atoms are hard, and not because charges repel. Because your electrons and its electrons cannot occupy the same states, so pushing them together forces waves into shapes with sharper curvature, and sharper curvature costs energy, and the cost is paid as resistance under your back. The floor beneath the bed holds by the same accounting. So does the crust of the earth. So did the star that failed to collapse. You are lying on a refusal. Inside your cells, tonight, small things are passing through walls. Enzymes are moving hydrogen atoms across barriers that classical chemistry says they cannot cross, at rates measured in laboratories and set by a constant with 33 zeros after the decimal point. Your liver is doing it while you rest. Your muscles are doing it. The repair machinery reading your DNA is working along a molecule whose two strands are held together by protons sitting in double wells, and whether any of them are tunneling tonight is a question nobody has settled. The barrier is there. The shape of it is exactly what the equation describes. Whether it matters to you remains unknown, and the people who study it will tell you the same. There is a glass of water somewhere near you, or there was earlier. Each molecule in it is bent at about 105 degrees, and it is bent because of the shapes the electron waves are permitted to take around an oxygen nucleus, and for no other reason. Change those shapes and water would be straight, and ice would sink, and the lakes of this planet would have frozen from the bottom up every winter, and nothing would have survived in them. A bond angle, set by a wave fitting into a landscape. Every membrane in you is held by bonds that exist because an electron, given 2 nuclei instead of 1, has room to spread. Every heartbeat depends on ions crossing pores whose fit is set by energy levels. The warmth of your chest under the blanket is molecular vibration, quantized, stored in steps that 100 years of experiment have counted. And the oxygen you are breathing is bound, right now, to iron atoms in your blood, held there by the shape of an orbital, carried to the cells that need it, released when the shape shifts. 4 of them per molecule of hemoglobin, 250 million molecules per red cell, 25 trillion red cells in you. All of it a solution to the same line. None of this is happening to you. It is what you are made of. A dust grain, floating in a sealed and darkened room, cooled almost to absolute zero, still cannot hold a superposition for longer than a second because photons from the birth of the universe pass through it and carry the information away. You are enormously larger and enormously warmer than that grain. The photons pouring off your skin, thousands of trillions of them every second, are carrying the record of exactly where you are, out into the room, into the walls, into everything. The universe is measuring you, continuously, without ever intending to. Which is why you are only ever in one place, and why you have only ever had one history to remember. The equation never stopped applying to you. Contact is what makes you singular. Somewhere in the sky above this roof, hydrogen is glowing at 656 nanometers, in clouds between the arms of galaxies, whose light left before the Earth had oceans. It is the same red we met hours ago, produced the same way, by 2 energy levels beating against each other at a frequency the equation fixes and nothing else can change. The atoms out there did not consult the atoms in here. They had no need to. One line, everywhere, running without maintenance, for 13.5 billion years. I want to say one thing about not knowing, before the night ends. We spent hours on a line of mathematics that predicts the magnetism of an electron to 12 decimal places, and we found, right at its center, a question nobody can answer. Why does one thing happen? The equation carries every possibility forward, faithfully, and it never chooses, and something chooses anyway, and no one alive knows what. The people who built the theory could not agree. The people who use it every day to design the machine in your pocket do not need to agree. The disagreement is 100 years old and is not embarrassing. It is what an honest science looks like when it has reached the edge of what it can currently say. You do not have to resolve that to fall asleep. Nobody else has. Erwin Schrödinger died still unhappy with the meaning of the letter he chose almost at random, and in the meantime his equation kept the atoms of his body together, exactly as it is keeping yours together now, indifferent to whether he approved. Understanding was never the price of admission. The waves in you were fitting themselves into the shapes their landscapes allowed long before anyone in your family line had a word for a wave. They are doing it while you drift. They will do it through the night, at a rate set by a constant, without supervision, without any need for you to attend. There are machines near you that were designed with this line, by people who never once wondered what psi is. The phone charging on the table moves electrons through barriers on purpose to hold a photograph you took of somebody you love. The small light on it glows because electrons drop between levels in a crystal, and the color of that glow is the size of a gap, and the gap was chosen by an engineer solving the equation on a screen. None of them needed the meaning. The specification was enough. A century of civilization has been built on a sentence whose subject nobody can identify. So let the room stay dark. Somewhere below the level of anything you can feel, 100 billion arrows are turning, each one keeping its length precisely, each one refusing to grow or shrink, and that refusal is the only reason there is anything here at all to lie in this bed. They were turning before you closed your eyes. They will be turning at dawn. Nothing about their turning depends on you watching. Thank you for spending these hours here with me, and for the patience it takes to follow an argument from a screen full of dots all the way down to a line that a man wrote by hand in the winter, and for staying through the admission, at the end, that we still do not know what it means. That is a rare kind of company, and I am glad of it. Sleep well. The arrows will keep their length. Good night.